Welcome everyone to our FDL 2021 showcase. I'm Sarah Jennings and I'll be your host today as we go through this amazing program. We have today a jam-packed agenda where we're going to be going through our FDL challenges this year that cover Earth science, astronaut health, heliophysics, and planetary science. We're also going to get the opportunity to interact with some of our FDL partners as well. But before we dive into the program itself, I'd like to introduce my co-host and CEO and president of the SETI Institute, Bill Diamond.
Great. Well, thank you very much, Sarah. Good afternoon and good evening to all of you. Thanks so much for joining us for today's FDL 2021 showcase. Please buckle up and prepare to be amazed. So I'm Bill Diamond. I'm the president and CEO of the SETI Institute. We're a nonprofit research and education institution where our mission is to lead humanity's quest to understand the origins and prevalence of life and intelligence in the universe, and to share this knowledge to inspire and guide present and future generations. We've been managing and administering the FDL program since its inception 6 years ago as an initiative launched by the Office of the Chief Technologist at NASA headquarters. The program was designed to explore the potential for AI and machine learning techniques to enhance and accelerate NASA science in basic research domains. NASA was also interested in evaluating the efficacy of interdisciplinary teams of computer scientists and domain scientists working together in an accelerated research sprint environment to tackle specific science challenges and questions. Also, FDL was intended to leverage public-private partnerships to help advance human knowledge and understanding of critically important natural phenomena. So 6 years and more than 50 AI ML workflows later, with a thriving partnership of more than 16 leading academic, government, and private industry partners, we're really delighted to be sharing with you the work of this year's 7 research teams. Our FDL researchers, supported by their mentor faculty and various partners, have not only demonstrated significant advances in their domains of research, but also in the development and application of state-of-the-art AI and machine learning tools. So FDL is truly open science and exploration for all humankind. Today's presentations are a culmination of 8 intense weeks of research, which mark the execution phase of a year-long program that includes challenge proposal solicitations and selection, participant application and researcher selection, mentor and faculty recruitment, team formation, partner engagement, program design, relevant data set identification and acquisition, and an AI/ML bootcamp, which kicks off the 8-week sprint. So following today's showcase event, the teams will continue working on their results for presentation at scientific and AI/ML conferences, and in some cases, also publication in peer-reviewed journals. FDL results are also written up as NASA technology memos and published by the FDL program in an annual proceedings document. You can follow the further progress of this year's teams and obtain copies of the proceedings when they're ready by visiting the FDL website at frontierdevelopmentlab.org. And with that, Sarah, let me turn the podium back to you to share a bit more about the execution of the FDL program and some of its achievements over the past 6 years. Sarah?
Great. Thank you so much, Bill. So I just wanted to share a little bit more about FDL in the numbers. So we have had 6 years now. We have over 18 partners, and excitingly, we've also been able to utilize over $4 million of compute. We have over 1,500 alumni, and it's really just been an exciting and growing program. We also have a growing number of challenges that we've been able to tackle in various different categories. So we've looked at challenges in astronaut health. We've looked at challenges that seek to know, are we alone, that deal with exoplanets and astrobiology. We've also looked at mission control for Earth, living with our star and heliophysics, the moon for good and our lean resource challenges, as well as planetary defense. And we're excited this year to be continuing to grow that capacity with the challenges that you will see today. We also have been making a concerted effort to make sure that the work that we're doing is shared with the public. As Bill mentioned, we have open science and we truly believe in this. So we've created SpaceML and we're working to put tools, data sets, as well as the algorithms on this platform to be able to make it publicly available to continue the research. I want to acknowledge that things look a little bit different than they used to. We used to be hanging out in the SETI Institute or some of our various partner locations, but now we are all virtual. So this was our previous team photos, and now we have created this amazing virtual team with people around the world. And it would not be possible if we did not have Google Cloud. So Google Cloud has been an amazing supporter of our FDL research and has provided a ton of compute for our researchers to take advantage of. And it's been especially amazing in this virtual and remote environment to be able to utilize Google Cloud. So I would just like to say thank you to them. And then I just want to switch gears a little bit and talk about our Y panel. So as we go through today's events, we're going to have Bill hosting our Y panels. And we have a number of our FDL partners and contributors and community members that are going to be joining us. Scott Penbrithy is going to be joining us for all of the different panels, and then we'll have rotating members that will be able to provide feedback about the team's challenge work that they're going to be presenting. And so Bill will introduce those individuals as we go along. And with that, I'm going to turn it back to you, Bill, to invite up our first speaker.
Great. Well, it gives me great pleasure to ask our longtime FDL colleague and supporter and today's kickoff speaker to get the program going. And so I want to introduce Dr. Lika Guhathakarta from NASA. Lika is a heliophysicist and a senior advisor for new initiatives at the Goddard Space Flight Center and is a heliophysics division program scientist at NASA headquarters. And Lika has been just an amazing partner and supporter of the FDL program for the last 4 years and has been truly an inspiration to all of us. So Lika, why don't you take the podium and kick things off for the FDL 2021 showcase.
Thank you so much, Bill and Sarah, for all you have done. First of all, a hearty welcome to all of you on another exciting year for FDL 2021. And yes, you have already heard, FDL is 6 years old. So in my way of thinking, it's just graduating from kindergarten and taking its first steps to grade school, already showing great promise of getting into a magnet school. Many of you know what that is if you have raised children. It has been a really successful program bridging the gap between scientific and technical advancements. The FDL formula, it's research talent plus challenge and data, capital and capacity. It is a culture of where anything is possible, and I kid you not. And you, the team that make it possible. Let me start off by congratulating the 7 FDL teams this year: 2 Helio, 3 Earth Science, 1 Astronaut Health, 1 Lunar Resources, for another successful research sprint, and acknowledging that for the second year in succession, the teams had to work entirely virtually, never in person together, adding a significant sort of burden already to an challenging program that exists. And all the same, FDL somehow got better at this management structure, really by creating interaction over Ether amongst researchers who were strangers to each other just 2 months ago. So yes, COVID has created endless griefs for so many of us. But this new way of bonding, with your peers and creating cutting edge science and technology tools stands out as a positive benefit for the COVID environment. I'd like to thank our partners, starting, of course, with Google Cloud, who provide the cloud compute resources without which the program would really not be possible. The reason the early career teams can make such tremendous progress in 2 months depend hugely on being able to experiment with large amount of cloud credit. Cloud technology is a game changer for managing complex ML pipelines, and we are getting more and more into it as years go by. And I'd like to thank all our other partners: Luxembourg Space Agency, USGS, Lawrence Berkeley National Lab, University Corporation for Atmospheric Research, DOE, MIT, Intel, Lockheed, Trillium, IBM, NVIDIA, I should have made a rhyme of this, Mayo Clinic, Planet, and of course, the SETI Institute in partnership with Ames. And this list keeps on growing. And I'm sorry if I missed any institution out. FDL really has created this ecosystem with public-private partnership, not in big ticket items like building rockets or spacecrafts, but really bringing the multidisciplinary research community to accelerate discovery of science and exploration. The importance of interdisciplinary teams in all these efforts really cannot be overemphasized. Pursuit of science and exploration research, in my way of thinking, is a combinatorial component, has a combinatorial component, encompassing threads of science and technology separated by often traditional, boundaries of funding and academic labels. There are many types of scientists and engineers, physicists, astronomers, biologists, computer scientists, at least one for every type of problem that you can think of. Some problems are so big and complicated, both from data and a domain perspective, that no one type of researcher is enough to solve them. NASA and other agencies have long struggled with such problems. Of course, it comes with the territory. To fully understand the scope of the big data that NASA and other agencies bring to the table, it is really necessary to apply the intellectual tools of astrophysics, heliophysics, earth science, planetary science, biological sciences, spacecraft design engineers, data compression, and much, much more. Such understanding is best developed, I believe, in the context of a crowd. That is, a crowd of researchers. Now, you have heard of crowdfunding. FDL, I believe, has pioneered what I think is crowd thinking. 6 years ago, we kickstarted a new concept called Frontier Development Lab. And it works like this. To create synergism, FDL has created the summer sprint that you're going to hear about, approach where members from different disciplines meet for the first time, typically, in this case, of course, virtually. FDL paired science and computer engineering, early career doctoral students with experts from the space agency, academia, and some of the world's biggest technology companies. Partner companies contribute various combinations of hardware, algorithm, supercompute resources, funding, facilities, and subject matter expertise. FDL views enhanced data outcomes as having equal value to the algorithm. That's really kind of a shift in our thinking. And thanks to our domain specialists and data providing partners, every year we learn so much. FDL creates numerous assets of value to the community, such as pre-processed and enhanced data, as well as skilled ML researchers able to integrate their ML skills into space careers. A great benefit to an organization like NASA and the country at large. Anymore, robust uncertainty quantification is crucial to trusted workflows that is created. Thanks to our ML faculty members, so rare and so dedicated to the work, trust and reproducibility are becoming key to greater adaptation of ML workflows in basic research, where robust uncertainty and quantification is becoming crucial. And finally, I'd like to say that we want to dispel the notion that AI is magic by learning how to maintain and improve it. And possibilities for the space program, basic research, exploration are enormous. After all, remember, AI is just fancy statistics. FDL challenges are often keystone capabilities to broader investigations, which unlocks the potential for mission-enabling development, science data discovery, community tools and resources, and advanced method development, as you will soon see. I wish the teams good luck with their closing presentations. Thank you.
Great. Thank you so much, Lika.
Thank you, Lika. That was inspiring. And I think we're on to a new thing here with crowd thinking. A great concept, and maybe it adds a new dimension to crowdfunding. So with that, Sarah, I guess we're ready to move into the presentations. Am I right?
Yeah, and I'm actually getting reports, Bill, that it sounds like some of our audio might be sped up. So I guess they're really just interested in getting us to the FTL challenges. So if you're viewing from the audience and you hear it sped up, we're going to work on that. And yeah, Bill, I think you have some people that you'd like to thank for this next section.
Right. So we're going to start by introducing the first of our presentations. The first of our presentations from the FDL teams is Astronaut Health Space Medic. This is about the causal inference for out-of-distribution generalization using machine learning to improve our understanding of the cellular level dynamics induced by radiation exposure, potentially enabling enhanced early diagnostics of various cancers. And for this team, we had several partners, as is the case with all of our teams, starting, of course, with Google Cloud. And I think Lika put it correctly when she said that without the support and incredible compute resources provided by Google Cloud, the FDL program would really not be possible. And just by way of quantifying that in some respect, the amount of compute that we have used this year compared to what was used in the first year of the FDL program, it's increased by 700 times, not 7 times, 700 times. So massive computing resources being applied to support the teams and enabling fast iteration and real-time on-demand access to incredible compute. So thanks again to Google Cloud. And our other partners for this program, for this first topic, include the NASA Gene Lab, Intel, and the Mayo Clinic. With that, Sarah, I think we have a video to kick off the first presentation.
Yes, we do. We're going to be having Sylvan that's going to be sharing an introduction for the team. So we can go ahead and play that video.
In the vacuum of space, astronauts are exposed to cosmic and solar radiation constantly. This can damage cells and surrounding tissues, leading to mutations and inflammation. Such systemic responses are precursors to cancer, vision impairment, or disruption of the central nervous system, just to cite a few known effects. This is a limiting factor in our ambitions to establish a permanent base on the moon and one day, hopefully not too far away, send human explorers to the surface of Mars. While the link between radiation and cancers has long been understood, machine learning has the potential to help us understand the specific molecular drivers of cellular damage in space radiation exposure, and do it in a way which is private and secure, the way all patient data should be. I am therefore pleased to be able to introduce the FDL 21 astronaut team.
Hello everyone, it's my pleasure to introduce the Astronaut Health team. My name is Owen and I'm an MD PhD student studying health data science at Oxford. Over the last 8 weeks, our work is focused on bringing together 3 areas of research: causal inference, federated learning, and domain generalization. I'll explain what each of these mean in the presentation. But first, I'll introduce the team. I'm one of the 4 researchers on this year's team, and my fellow researchers are Paul, Giuseppe, and Linus. Supporting us have been our amazing faculty from NASA, Intel, and the Mayo Clinic, last year's Astronaut Health team, and last but certainly not least, our team leads, Lauren Sanders and Frank Sobachensky. Our work this summer is motivated by the biological challenge of spaceflight, and specifically cosmic radiation. This radiation can penetrate through thick layers of shielding and body tissue, and on a 7-month trip to Mars, it's cause for concern. Cosmic radiation is carcinogenic, and if we are ever to succeed as a spacefaring civilization, this is an issue we must address. Understanding the exact mechanisms of radiation damage can give us huge insight into how to reduce and prevent damage. However, studying these mechanisms is difficult. This is as human space data is incredibly expensive to generate. The data we have is also incredibly siloed in separate locations. Furthermore, when data is millions of miles away in space, getting it all back to Earth is hard. There is, however, another data source, which are animal models. While this data is not exactly human, we can generate large volumes of samples without these siloed data issues. This brings us to our research question. Can we combine high-dimensional human and mouse data to learn about human radiation risks using data stored in different locations? In this question, I firstly want to highlight the idea of combining human and mouse data. This has been of particular interest in NASA, who want to make the most of the data they have in a combined setting. I secondly want to highlight analyzing data stored in different locations. This has been of particular interest for partners at Intel. I'll now hand over to Paul.
Thank you, Owen. I'm Paul Duckworth, a postdoctoral researcher at the Oxford Robotics Institute at the University of Oxford. As Owen mentioned, our project built upon last year's astronaut health team and enhanced the causal inference platform, CRISP, in various new ways, given new priorities from our partners. In total, we expanded upon the work in 3 directions. First of all, we expanded the causal machine learning methods in CRISP to cover a wider range of problems and data types. Secondly, to tackle the problem of siloed data sets, we developed a proof of concept pipeline to learn an ensemble of causal models without the need to move data between physical locations. Finally, using radiation exposure data from mice and humans, we investigated transfer learning between organisms to overcome the problem of small data sets in biological settings. We all know that correlation does not imply causation, and we wish to learn the causal features that can be used to predict even on out-of-distribution test cases or under distributional shift. We wish to identify the features of our dataset that are consistently predictive of a target across many different environments, such as in the example image shown here. These invariant features are then considered candidates for being causal features. Medical data is often siloed in different locations, so CRISP version 2.0 implements causal methods in a federated framework. Here is an overview of the federation architecture based on Intel's open source software, OpenFL. Starting on the left, we have a global model that can be used for pre-training or initializing parameters. This model is then shared with a set of collaborator institutions or users who each use the model and train one round of training on their local data sets. The models are then updated by the users and sent back to the aggregator to average the model parameters and reshare the new model with the users. All institutes train each model in the ensemble on their data sets, and no data is moved during the process. In summary, CRISP version 2.0 pipeline can be realized in either a federated or non-federated setting. It begins its life on GitLab, and it is fully Dockerized and outputs an ensemble of results to a front-end Streamlit application for further analysis and insights. I'll now hand over to Giuseppe to discuss our data sets.
Thank you, Paul. I'm Giuseppe from the Maths Department at Oxford. I will start by showing you how models trained in a federated way match those trained in a non-federated way. We validate this on synthetic data sets, which allows us to consider different known causal structures. In the shown plot, the y-axis corresponds to the expected ratio of causal features found when considering alpha elements. The higher a plot is above the random sampling line, the better. As shown, the federated implementations in the orange line perform as well as in the non-federated case, in the blue line. Now that we have validated the accuracy of federated methods, we can shift our focus back to the aim of the project, inferring causality relations for carcinogenesis with human and mouse data. Despite the differences in the biological background of the human and mouse data, we hypothesize that there might be a benefit to the performance of our causal inference methods by mixing them. Therefore, we make the human and mouse data coherent by identifying genes with similar structures and function between the two organisms. To that end, we utilize the Ensemble database, maintained by the European Molecular Biology Laboratory. I will now hand it over to Linus, who is going to walk you through the results of the biological data.
Thank you, Giuseppe. I'm Linus and I'm a PhD student in computer science at the University of St. Gallen in Switzerland. I would like to highlight some of the most striking biological results that we obtained with CRISP 2.0. To overcome the issues of small data set size and to improve generalization capabilities, we ran a set of experiments to understand how our models performed when using varying degrees of human and mouse data. Using all available human transcriptomic radiation exposure data, we progressively added mouse data until the mice outnumbered the human sample points 2 to 1. What we find is that our results are strikingly consistent at different levels of blended data. The figures on the right show how much concordance there is compared to 100% human data in the top 10 and top 20 features that our models predict. These results suggest that for experiments studying the effect of gamma radiation on blood, it is possible to blend human and mouse data in causal inference settings to still identify human relevant features. Therefore, I would now like to showcase one result obtained on this blended gamma radiation exposure data. We used linear IRM, a causal inference method that is part of CRISP, to identify genes with invariant relationships across environments to predict the radiation state. The absolute coefficient score, seen in the blue bars, corresponds to how certain the model was of an invariant and causal relationship to the biological effects of radiation exposure. Checks with the literature reveal that our models function as intended. The identified top factors are strongly linked to cancer in published articles. Of particular interest is that we could not find published research on a top scoring gene. This suggests that there may be value in studying this compound in more depth. In summary, the FDL Astronaut Health project this year showcased the utility of causal and federated learning on biological data to advance our understanding of space radiation risks. We investigated approaches like the merging of human-mouse data to deal with low sample sizes, and also performed comprehensive validation on synthetic data sets. On top of that, we also presented a working prototype of a federated ensemble of causal machine learning methods. There are still some next steps that we aim to tackle in the future. These include new approaches for causal feature weighting, the inclusion of more causal discovery methods, as well as applying our federated workflow on real-world distributed data sets. Thank you very much for your attention.
Amazing. Thank you so much, Astronaut Health. That was fantastic, and you set the bar very high. So now I'm going to go ahead and turn it to Bill to start our Y panel and introduce our panelist.
Great, thank you. Well, again, to echo Sarah, that's a wonderful, wonderful job, but an amazing continuation of the work done last year in the development of the CRISP tool. And I think the implications here are amazing. To share this little review with me, we have Scott Penberthy, who is the Chief Technology Officer at Google Cloud, and he joins us today from Lake Tahoe in sunny and smoky California. And also with us is Shashi Jain. He is the Tech Innovation Lead for Health Solutions at Intel, and I believe he's joining us from up in Portland. So Scott, starting with you, what are the implications here in terms of real-world applications and improvements to things like early diagnostics in medicine with the work that this team has done in the area of causal inference?
Well, I think it's this is where it's at in medicine, Bill. And I think we're seeing now that we're talking a lot about precision outcomes. It's producing a fountain of Nobel laureates and national medal winners these days. And I'm just curious, maybe for the team itself, because I've been following some of the work. It's been like Chris Mason and whatnot, and looking at tardigrades and how they have these suppressors, the D sub protein, if you will. I was curious, if you look at what's happening in the humans and the mice, are there things that are helping repair our DNA that for like what happens for sun radiation and whatnot? And are you starting to find those genes in in your analysis? And then the second part is, I love this this statement of it's correlation is not causality. And it's very interesting, and I like your insight to say what's invariant between the environments. Maybe those are the things that actually lead to causal inference. So that's a bright insight. So I think there's no shortage of people who are very interested in your outcome. But I think just your opinion of like, what are you finding versus the work around DSPA, if you're familiar with that, and how might those two relate is my question.
Wonderful. And Shashi, can you tell us a little bit more about Intel's federated learning technology, and which was clearly a big part of this? Would you describe what this is and what your vision is for federated learning?
Yeah, certainly. So federated learning, again, is a technology where you can train an algorithm on data that's siloed or heavily protected, or that needs to be kept private. And astronaut data absolutely fits the bill. There's only a few astronauts that have gone into space, and their data is highly protected. Similarly, mouse data from the Mayo Clinic, and there's many other sources. So what federated learning allows is for the algorithm to go to the data versus the data being aggregated together to train the algorithm and then improve it over time. So the federated learning software is this is an open project, open source project. You can check it out on GitHub if you'd like. But the vision here is to enable many more collaborators and increase the pace of innovation where there are these data silos. And what I'm excited about in this, in the approach that this team took is they not only proved that a federation could be set up very quickly. In fact, they set it up probably quicker than I did on my own bench. It was great to see that, but that they could increase the number of collaborators that have. Admittedly, there's going to be very few that have astronaut data with radiation testing, but now they've opened up to different kinds of data. Collaborators that have radiation testing data elsewhere, and then they've developed a system that can increase the pace of innovation. So the operations side of this, I think, is just as important as the research side here.
Absolutely. And by the way, Shashi, I want to point out for all our listeners that we do ask all the mice to read and acknowledge our privacy policy where their data is concerned. So it's not just about the astronauts. Scott, a closing comment here. What for you is a key takeaway from this team's work and what they presented to us today?
Wow. It's just wow. It's such brilliance, and what you did in 8 weeks, it's not worthy. That's a heck of an accomplishment in the period of time. And I think you are on the cusp of what's happening in research and medicine. And I look forward, maybe one of you or all of you will at some point crack into the Nobel Prize. So I'm really interested to see where you take this.
Wonderful. Thanks. All right, Sarah.
All right, so now we're going to switch gears and we're going to go to our natural satellite, the moon, and we are going to be having an inspiring video from our partner, as well as moving into an introduction by Mark Shirley. So we can go ahead and play those videos.
I think I always have been looking at the sky, especially the moon. We're going back to the moon. The idea is in 2024, the first woman and the next man on the moon.
He said on time, I think.
This time we want to stay on the moon. We want to have people on the surface that live there, that work on the moon. You can see the moon as a stepping stone for us to go to other places in the solar system. Our challenge was, if you want to build a base, you want to have metal to build structures. FDL is a unique opportunity to bring together scientists, and we have these 8 intensive weeks where we just sit down and work hard every single day. A sprint is a science sprint, if you want. Our goal is to create a map of the moon that tells us potential locations of metal, which we could use for our base in the future. We use data from 6 different spacecraft. By combining these data together, we create a new powerful data set for machine learning-based anomaly detection. As we combine data from spacecraft, 42 different layers, that sums up to about 35 terabyte of data. We basically drown in data. And if you want to crunch these numbers, you need big compute, and that's where Google Cloud comes in. We were able to build our own machines with 200 CPUs or more. Intel provides these CPU cores that Google Cloud uses, And what we did in our project is to collect all these maps, stack them on top of each other, basically creating a massive database. We could spend years and decades to try to understand the data, but thanks to the AI and machine learning, can tell us the answer in a couple of days. We can actually understand the data with labels that tell you, here might be metal, here might be metal, here's probably no metal. We can achieve amazing results.
NASA will soon be returning astronauts to the moon, this time to stay. Because of this, the search for and study of water ice on the lunar surface is of critical importance. When it comes to volatiles and water ice, one of the most interesting areas is the South Pole. We'll need maps for both rover and human explorers. Machine learning offers the potential of enhanced resolution images of this region, providing vital information for future rover and human traverse mission planning. But there's an important catch. We also need good evaluation metrics for the results to be trusted. To tackle this problem, I'm delighted to introduce the Moon for Good 3 team, Upscaling Lunar Resources.
Hello, everyone, and welcome to the Upscaling Lunar Resources team presentation. My name is José Ignacio Delgado, and I'm here with my teammate Paula Harder to introduce Anubis, the solution that we have been developing during the past 8 weeks here at FDL. But before getting into the solution, I would like to talk a little bit about the context, even though we saw an amazing video just now. So even though Mars had been on the picture for quite a long time, we are going back to the moon. Humanity should return to the moon, and this time we want to stay there. So here at FDL, we want to provide some help to achieve this goal, as we can see here. And there are plenty of missions that are going to be happening on the lunar surface in the upcoming years with many objectives, such as scientific research to, for example, understand better the origin of our planet, lunar resources detection and extraction, where we process ice, for example, to be able to keep astronauts on the lunar surface for a longer time, and also solar system exploration, as we will be using the moon as a stepping stone to go to other places in a way more efficient way than what we are doing right now. Okay, so in order to plan all these missions, one key element are like the lunar surface images, in order to understand what's on the lunar surface and which places are most interesting for us. And the greatest database that we have available right now is the one provided by the NASA's Lunar Reconnaissance Orbiter mission. So this satellite has been orbiting the moon for 12 years now, and it's providing a lot of data, such as this image that you can see here. Images from the lunar surface, so now the whole moon is mapped actually in this database. But there is a little problem with these images. So the resolution of the images is depending on the altitude of the satellite when the image is taken, and also the lighting conditions at this moment. So let's take a look at the southern hemisphere. So we can see here how, for example, if we look at images with 1 meter per pixel resolution, there are plenty of them. There are the orange dots here. But if we look for images that have a higher resolution, let's say 0.5 meter per pixel, there are not that many, especially on the core of the South Pole. That is the target for the upcoming mission that I mentioned just a minute ago. So this is the problem that we want to help with. This is what our solution was focusing on. And here is an example of what does it look like at 1 meter per pixel image. So this is the Apollo 16 landing site. And we can see here how the features of the lunar surface are not really clear. But if we go to 0.5 meter per pixel, we can see clearly where the craters are and where like the obstacles for example, a potential navigation on the lunar surface can be. So let's say that we want to do some traverse planning for a rover in the lunar surface. If we are working with 1 meter per pixel resolution, it's going to be a hard task because we are not sure where the obstacles are. But if we transition to this 0.5 meter per pixel resolution, we can see clear where they are, and then we can navigate safely in the lunar surface. So this is the problem that we tackle, and therefore we go to our actual application, Anubis. Anubis stands for an adversarial network for uncertainty-based image super resolution. And again, it's the one that we have been working on for the past week. And now I'm going to let my teammate Paula go through the solution and also like the results that we have gotten so far.
Thanks, Jose. Welcome from my side. So I'm going to introduce Anubis now. The core of Anubis is a residual neural network, the generator you see here. It gets a low resolution image as an input and generates a high resolution image. But to train this network, we need pairs of high-res and low-res images. And we get them by looking at sites where we actually have high-res images and then downsample them to get their exactly matching low-resolution counterparts. When we train the network, the generator, we introduce the discriminator and they play an adversarial game against each other. The discriminator tries to tell the real low-res and the real high-res and the generated high-res apart, whereas the generator tries to fool the discriminator. This way, the output here gets better and better and closer to the real high-res. So what we get is a real high-resolution output image from the generator. We not only produce this high-resolution image, we also produce an uncertainty map along with it, using a deep ensemble method. It shows us in which areas of the image we fully trust our prediction and in which areas we might look into more detail or we want to stay away of. You can see here dark green means full trust, whereas a red bit would mean we are not very certain in this area, just here in the upper corner, and yellow is something in between. We applied our model to the Shackleton-Ridge area, an area of interest for the Artemis program, for example. It's an area very close to the actual pole, but there are no high resolution images there. So we looked at this 1 meter per pixel low resolution image, and it's hard to see detailed features. For example, in the zoom in, you can see here a big crater, probably a smaller one, but apart from that, it's very hard to see. Now we apply our model and we can see how we get much better features. We can see 2 craters here and like a big footprint shape in the zoomed in area. We validate our model, and for that we need real low-res and high-res pairs. We found a site where we do have both. So this is a real low-res pair from the LRO database, a real low-res image. We apply our model, and now you can see clearly how much more details and features we get. This is the Anubis output. And then we compare it to the actual real high-res image, and we can see how close we get with our prediction. It's hard to tell them apart. To make sure to show that our solution can be used for applications, we applied some path planning. You can see here how in the low-res image, the path which is taken to avoid obstacles takes a detour because we're not sure if we can traverse this area here. Whereas in the generated high-res, we get a much more optimal path, which is very close to the actual high-res path. To sum up, Anubis enables us to enhance images from all over the moon. We targeted the South Pole now, but the model can be adapted to any parts of the moon. It increases the resolution of an image by a factor of 2. And with this, we are able to detect and map hazards which are currently unknown. We not only produce those super resolution images, we also give an uncertainty estimation along with them to make it feasible for safety critical applications. We hope that with our solution, we can contribute to future lunar missions. We can help humanity go back to the moon, establish a base there, and go beyond. Our team here already made it to the moon. That's me, Paula, Jose, who presented before me. We're the 2 researchers. Then you see our great team leads, Sida, Miguel, Ben, and Valentin. And we want to thank our team advisors, Freddie, Mo, Jari, and Chedi, for their great help. And also our sponsors, especially Luxembourg Space Agency. Without them, this challenge wouldn't have been possible. Now we want to thank you for watching.
Thank you so much, Lunar team. Really awesome work. I'm excited to hear what words Scott comes up with, because wow. But with that, I'm going to go ahead and turn it over to Bill and our panel.
All right. Thank you very much, Sarah, and thank you, team. You know, these images and the work you've done remind me of all those things you see in the movie, you know, when trying to solve the crime. They're looking at some low resolution image of a car in the distance, and somehow they're magically able to zoom in on this speckled image and read the license plate. But, you know, that's the movies, and this is the real deal. Joining Scott and I to talk about this work is Brian Day. Brian is Deputy Staff Scientist at NASA Ames, and he's part of the Solar System Exploration Research Virtual Institute, or SERVI there. So welcome, Brian. And Brian, let's start with you and ask you, from your perspective, what are the takeaways here, and how do you see this work contributing to future NASA missions?
Well, this is very exciting work. Right now, there is a concerted effort amongst NASA and its partners to characterize upcoming landing sites as well as potential traverse paths. And as has been mentioned, the gold standard is the LRO NAC data. And our ability to do analyses are constrained by the resolution of that data. This work here has the promise of really opening that up and giving us a much finer view. And so I am very much looking forward, as I know a number of other people are, to be able to take the output from this super resolution work and be able to feed it into our AI tools for doing crater detection, boulder detection, and be able to do these analyses. These will allow us to really make the bold moves to explore this very new and different terrain.
So, you know, the FDL program has done lunar resource work. You know, the metals mapping that were done as part of last year's program, and now these permanently shadowed regions and the image enhancement there. What would you say you'd like the teams to focus on next year? What's the next stage for this work going forward?
Is that to me?
Well, I was going to ask Brian. I've got another question for you, Scott.
Oh, this is Brian. I'd go to Brian. He's
one thing I'm very, very intrigued by. Of course, so one of the things that, of course, we're very intrigued by the NAC data that is then the new features that are going to be revealed. But the potential for this technology to be applied to other data sets is also really fascinating. One of the things I look forward to seeing is, for instance, seeing this applied to the lunar orbiter image recovery data, and being able to now look at temporal changes in the moon, on the surface of the moon. That really is exciting. And so this technology applied to the NAC data is wonderful, but it has applications that could go well beyond that.
Yeah, absolutely. Scott, I was going to ask you about the AI and the ML. You know, this is one of those areas where the AI tool does look like that black box. It looks like this magic thing that takes this low resolution image and turns it into this high resolution image. And of course, the team talked about the training sets and so forth. But how does that work, and how do we, you know, we trust these enhanced images?
You know, I can't help but think, Bill, I'm reminded of a few centuries ago, someone started thinking about physics and optics and curvature and material science, and those were glasses. And I think, you know, for Ben Franklin. So I think what you all are inventing here, I think is a very powerful, like, well, I wear glasses, we all wear glasses. I think as you think about exploring the heavens and we go out, our instruments need the same. And it has to do with physics, because you can't backhaul, as Brian knows, you can't backhaul high-res images from Mars or from other you know, moons. So what you have to do is, you got, just much like the eye, only where you need in high uncertainty should you have the high res. Everywhere else you could just sort of use prior probability distributions, kind of like, you know, we kind of know where things are. And I think that is sort of a brilliant step forward in that. And I see this sort of technology becoming as commonplace as eyeglasses for every instrument, for everything we explore. Because what's really neat about this is that it's using a neat technique looking at probability distribution. So if you see patterns before, and you know, one analogy I used to say is like, imagine I give you 7 different smiley faces. We all know what smiley faces are, right? The icons. And I give it to you in really high res, 4,000 by 4,000. You see, it's beautiful. I go to Mars and I say, I just saw a frowny face. With that bit, with those couple bits of information, you can recreate something that's very close to what I'm actually seeing, right? Because you've got the prior distribution of you've seen it before. And I think the work you're doing, Paula and Jose and Piotr, of actually looking at that, how do you fuse those sensors? Start thinking about other sensors you can fuse, and then how do you make an iterative system so that when you have uncertainty, then go query the instrument to get a higher res one, and that becomes like an active eye. And that's the kind of thing, if you put that in Brian's hands, oh my goodness. I mean, because it allows him the ability to see from afar with, with the physics that has these limitations. And that to me is just a fundamental advance in science and eyeglasses for exploration. It's awesome.
Yeah, fantastic. Well, speaking of eyeglasses and lenses and optics, so with the next topic, we're going to turn our lens from the moon back to Earth. But here we continue to build on this notion of how powerful AI and machine learning tools and techniques are for processing and dealing with and or possibly describing images and image data, of which there are massive amounts, particularly when we're talking about NASA resources. So the next topic up is the automated reporting of natural events. And this is about using satellite imagery and metadata, where we leverage natural language processing to help scientists better manage and disseminate the vast quantities of space imagery that are used to help predict and respond to large-scale catastrophic events. And our partners on this are the NASA Marshall Space Flight Center and NASA's Earth Observatory Group, and once again, of course, Google Cloud. So with that, Sarah, let me turn it over to you. I think we, again, have an introductory video.
Yes, we're going to hear from Raul, who is going to introduce the next team. So we can go ahead and play that.
Every day, hundreds of natural events happen all around the globe. Fires, hurricanes, thunderstorms, earthquakes. These all can be seen from space. Reporting on all these events is a time-costly task. We asked, could we leverage a new natural language processing techniques to provide NASA authors a tool to help facilitate the reporting of natural hazards and phenomena? This project is challenging, but the success will have scientific and societal impact, helping NASA's Earth Observatory inform the science-attentive public about natural events in a much shorter time frame. It is with this context, I'm very pleased to introduce the team behind automated reporting.
Hello, everyone. This is Vasiliki from the Automated Reporting team, and I'm glad to kick off the presentation of our project for FDL 2021. Our research team is composed by Fexen, Vishwas, Noah, and myself, and we are fortunate to be advised by great faculty, Piotr, Kevin, Deepthi, Kumar, Frank, and Raul. Our home Earth suffers from extreme events every day as a result of climate change. Wildfires in Turkey, hurricanes in southern United States, drought in South America, and extreme floods in Central Europe are only a few examples of such events. As time goes by, such events are going to intensify, which means that we need to take action. The need to report, educate, and raise awareness about such events is even more urgent. NASA Earth Observatory serves these aforementioned rainfall needs, as it provides information about natural hazards, disasters, and events of natural significance. Here is an example of an article in NASA Earth Observatory website that conveys important information about the destructive Hurricane Dorian. To sum up, all around the Earth can occur every day numerous critical events, from east to west, from floods in central China and Europe, droughts in South America, Brazil, hurricanes in southeastern United States, and wildfires in California. The more the events pile up, the more urgent is the need to assist writers and the reporting procedure. And here is where the automated reporting team of FDL 2021 has joined forces. And with that being said, I'm going to hand it over to my fellow researcher, Fexen, to talk about the data and our challenge.
Thank you, Vasiliki. That's right. There are so many events to write about. First, when a phenomenon is detected from the satellite images, it goes to NASA EONet, where it contains the set of metadata related to the event, basic important information such as location coordinates, date of the event, and sensors used to capture the image. On the right is the corresponding example narrative from NASA Earth Observatory, which contains the metadata information. Here's the zoom in on one of the paragraphs in the story. In our NASA Earth Observatory dataset, the average number of words in relevant metadata for a story is around 28, while in a piece of narrative, the average number of words is about 250. So one can imagine the approximate number of words in context that we will need to automatically build a story. And it's not just any story that we want to generate, but a story which will be specific to the respective event. And that is a challenge. Now I'll hand it over to Noah to talk about our machine learning pipeline.
Thank you, Fexen. So natural language processing, generally speaking, the application of machine learning to human language has experienced significant growth over the past decade. One especially big reason for why is the introduction of the transformer. This specialized deep learning architecture is known for something called the attention mechanism, which allows for fast and effective processing of sequential data like text. These transformers have been especially capable as something called language models. You've probably encountered a language model before. You can use them to translate a sentence, predict what you want to say in a message, filter the sentiment of comments or reviews, or summarize a paragraph into a single sentence. In our case, we are pushing this kind of model to the limit by synthesizing reports about natural events. To undergo this task, we use and modify recently published language models. These models are primed using text found on the internet like Wikipedia, whereas here we're only interested on text associated with Earth science. The outcome of this work is our model dubbed the Earth Science Transformer, ESTR for short, which allows for the ability to generate and more generally work with Earth science-focused text. But we don't stop there. Utilizing the versatility of language models, there are many applications for ours. We show it possible to train ESTR using automatically extracted conditions from NASA Earth Observatory and use those conditions as inputs to generate the kind of narratives we're looking for. To further refine these reports, something we have proven to be useful as well is to continue training on a particular event type, giving the model even more information about such phenomena. In this way, if you wanted to generate a story about wildfires and pay special attention to that, this approach will do just that. To demonstrate these results, I'll now hand it over to Vishvesh.
Thank you, Noah. So let's now see some result. We will see from the example that how our model has generated the acceptable result for the event that happened recently. The given example is about the wildfire that happened in California. As you can see on the left is our model input. We pass the title with its metadata and summary along with the keyword extracted using the name entity recognition. All the texts are then passed to the Earth Science Transformer model as an input, and the model generates the narrative. It's amazing to see how the generated output narrates the smoke and a fire event that happened in California. Highlighted in the bold are the date and the location. For example, August 20 and Sacramento Valley, which are correctly captured by the model. It is also interesting to see that the model can understand the event type, which is fire and smoke. Moreover, it also talks specifically about the sensor name like MODIS and NOAA satellite by which the data was acquired. So now the question is, how does the system works in deployment? Well, we have designed a system where first the writer will insert the key information like metadata, story title, and summary by either inserting manually, or the system will fetch all the information from references. Following that, as you can see in the output, our model generates the different narrative from the various models. In the end, the writer will select the most likely one or the best narrative of their choice. In addition to that, they can also write their own paragraph and manually input the new narrative. We collect the feedback for the given input and whichever result was selected to do the further improvement of our model performance and conduct the analysis. As a part of our contributions, First of all, we will provide a collection of machine learning models to NASA for a narrative generation. Along with that, we also plan to release our model open source via Hugging Face so that the public can directly use them. Secondly, we will provide a web application as well as APIs for inference and writing narratives. Moreover, we will facilitate the tool for a NASA, which will assist writer and at the same time collect the feedback and improve the models over time. We also believe that our models can be used in a downstream task like classification. For example, to classify a specific natural event in a given story. And hence, we will release the benchmarking dataset with a set task for the NLP community to open the problem to public. And last but not least, the team is planning to put all the resources as a one package and release the PyEster, our PyTorch-based framework with a proposed multi-data source training strategy for performing training as well as evaluation techniques for machine learning models for narrative writing. And with that said, I will wrap up our presentation by saying thank you to FDL and NASA for providing the opportunity to work on this project. And on behalf of the entire automated reporting team, we thank everyone for joining us today.
Great. Really well done, automated reporting team. And I'm going to go ahead and bring back up Bill and our panel for discussion about your work.
It's great. Well, another wonderful presentation and amazing work. And, you know, I hold NASA on a very, very high standard when it comes to developing acronyms. They're, you know, among the best of the best, in addition to their many other attributes. But I think the FDL teams are giving them a run for their money with things like Ester and PyEster. So this is great. So joining Scott and I for this panel discussion, we have Manil Maskey, who is at NASA headquarters and is a manager of Earth Science Data Systems. And also with us is Deepthi Karkata, deep learning software engineer at Intel. So hello, Deepthi and Manil, good to see you. And Manil, let's start with you and get your impressions on this work and its relevance to what you're doing in earth science at NASA, particularly in terms of, you know, how to manage all of the image data that's coming in constantly from NASA and other assets.
Yeah, this is very exciting. AI will be soon be able to tell stories, right? Specifically science stories. That's very exciting to us. So this, I want to give a little bit of context. Last year we ran a challenge called Knowledge Discovery Framework that looked into using AI to identify these events using our image archives, right? So we thought, hey, why not, once we detect those events, why not describe them, right? So that was the natural follow-on to that. And I think from what I see, great progress being made in 8 weeks, and we have a practical use for this. Not only just automating, but consistency, right? Hopefully, when AI is writing these stories, it's very consistent, right? It's not, let's say, I'm not saying it's by stories, but when AI writes, I think they'll be more consistent. And this is just the earth science example. There are events everywhere, right? In all other science domain. I think this is naturally extendable to other domains as well. And in terms of NASA, I think we've noticed that most of the researchers, especially early career researchers, right? They go into websites to figure out what they want to work on research-wise, and they naturally go and study some event and focus on those events, right? So this really provides this efficient way of cataloging these events and describing them, and hopefully provide more resources for those early career researchers.
Yeah, absolutely, definitely. You know, we talk about this a lot in the program. You know, it's not as though AI and machine learning are replacing humans or human activity in the sciences, but rather, you know, enhancing them and facilitating even greater insight. So that's really important. And Deepthi, what from your perspective, you were involved also working with the team and supporting their efforts. What were some of the big challenges you had to overcome, or that, you know, really presented puzzles in bringing this team together, and or not the team, but rather bringing these results together that are so impressive?
Yeah, definitely. So
So reporting of natural events is highly impactful in itself because it's bringing awareness about these natural events all over the world. But as you can imagine, automated reporting of these events is challenging in itself. Challenging because it has to infuse domain-specific information with general language to create fluent and easy to understand stories and narratives. So that's exactly what these researchers have done. So they've gone and gathered and accumulated data from different sources that are domain specific and put them together and build pipelines for training and evaluations of these models, and also work on robust evaluations of these models, I should say. So, and also a part of these resources are planned to be open sourced so that other researchers and the community can build on top of this work. So, it's a challenging thing, but it's commendable what the researchers have been able to do over the last 8 weeks. And it's creating pathways for like the community and other researchers to build on top of this work. So
yeah, absolutely. It's amazing. I mean, the idea that an algorithm could look at an image, have access to the metadata, and then write a story about it. Scott, is NLP going to change the world? Where are we going here?
You know, Bill, it's when I talk to my friends who are doing research in the climate crisis, they can looking at the fires, the floods, the drought, everything else. They're excited about figuring out how to really help us all. Yeah. Not one of them has ever said, you know what I love about this? I love writing reports. It's my favorite thing to do. And so this, to me, it's fundamental. You're now I love this team because you've taken one of the most advanced things in AI today, which is NLP and Hugging Face and these GPT transformers. And you're saying, let's get rid of the tedium. Let's go take this technique and then help you write the reports. You can do great science. I'll write the report for you. You can edit it. But I think what you're doing is you're uncorking the ability to accelerate science. And I think it's fantastic. And I think we're going to see this, Bill. We're seeing it now today with like Gmail. You can autocomplete a few words. Right. We're not that far off where it's going to write a draft for you. And I love the idea of applying this to science, especially on the climate.
You know, I love the fact that I don't have to type as many letters into my text messages as I used to, right? Because it predicts what I want to say next.
Yes, exactly.
Right.
And for scientific writing, it's a great idea. And kudos to the team.
It's brilliant. Well, congratulations to the team, and thanks again to our partners on that work. It's really terrific. And so here we have an example of machines aiding in the storytelling and description of scientific data, of scientific imagery data in this particular case. Now we're going to shift gears a little bit and talk about how AI and machine learning can also help us develop future understandings, predictive models of natural phenomena. I mean, so many of the earth science projects that we're talking about this year do relate to climate change, as Scott said, and we don't want to write reports about it, but it's also difficult to make predictions about it and what implications and impacts it's going to have on life and activity. So the next team up is called Digital Twin Earths, about our coastlines. And it's all about using machine learning to create a digital surrogate of coastal regions to help inform modeling and improve forecasting of coastal flooding events. And our partners for this are MIT Portugal, NASA Science Mission Directorate's Earth Science Division, Lawrence Berkeley National Labs, the US Geological Survey, and the Institute for Simulation Sciences, as well as IBM, and of course, once again, Google Cloud. So with that, Sarah, I think we have a video to kick this one off as well.
Yeah, but first we're also going to watch a video from one of our partners, and then Aaron from NASA headquarters will introduce the challenge. We can go ahead and play it.
At FDL, we're bringing together researchers who know a lot about machine learning and AI with researchers who really know the ins and outs of the problems that have a really big impact for the future of humanity. So I'm on the disaster response team. Floods are a really devastating natural disaster that impacts more lives across the world than any other natural disaster. Here in the United States, we're actually fortunate to have this stream gauge network. We have these monitors that tell us exactly how high a river is and how much water is flowing through an area. based on satellite imagery, can you actually remotely sense how high a river is just by looking at the top-down image? Specifically, we're focusing on tying satellite images to the stream gauge readings and seeing if you can predict the readings from the satellite images. And if we could do that, that actually increases our ability to do flood modeling in areas that don't have these physical stream gauges anywhere in the world that is at risk for experiencing floods. So if we have a model that gives us even a 30-minute additional warning time before this flood hits, in that 30 minutes we can get a family to safety. Google Cloud has really been what's made it possible for us to do our work on a day-to-day basis because of the amount of data that we can process. I think it's a really exciting time to be a machine learning scientist because more and more opportunities are appearing to apply these tools to really exciting problems.
Understanding how and why Earth's climate is changing is a passion of mine and something that is core to our mission at NASA. One area where climate change is already having dramatic impacts and will continue to do so in the coming decades is on our coasts, on which over 3 billion people live. Rising sea surface levels are making coastal regions more vulnerable to flooding. We are already seeing this in areas such as Louisiana, Florida, the North Slope of Alaska, the Maldives island chain, and Bangladesh. It is critical to understand flooding processes in coastal areas to understand predictability under various atmospheric and oceanic conditions. This is why I'm really pleased to be able to introduce this FDL project. Machine learning offers the potential for robust and reliable machine-learned surrogates for accelerating complex coastal simulators. In other words, a digital twin of our coasts.
Imagine you just bought a beach house in this neighborhood. How do you feel? Happy, right? But then a hurricane hits and flooding engulfs your home, endangering anybody that did not have advance evacuation warning. This scenario is devastating, yet unfortunately uncommon. Coastal flooding is considered one of the most significant dangers to humanity, affecting more than 1.5 million people and killing 8,000 annually. As climate change increases the rate and severity of extreme climate events, these numbers will only increase. And we want to save those lives. One way to do so is to make good flood predictions, which inform emergency response decisions, like evacuation orders. If your model incorrectly tells you not to worry, lives can be lost. If it suggests to issue an unnecessary evacuation order, trust is eroded. Accurate flooding predictions are pivotal, and we need research communities concentrating on this risk. And this is why we 4 researchers, supported by an accomplished faculty, have spent 8 weeks tackling flood prediction. I'm Konstantin, and I have a background in physics and machine learning, and you'll hear from Helga and Pesci, both earth scientists. Also, there's Nice from physics and machine learning. Now that we know why flood prediction is important, Helga will discuss its difficulty and our solutions to it.
Thanks, Konstantin. So at the present, there are physics-based numerical models that can simulate the ocean response to strong winds and low sea level pressure. They take over time wind speed, sea level pressure, and the bathymetry as inputs, and predict sea surface height or inundation height. However, running these physics-based models is computationally expensive. Due to time-consuming, today's predictions do not account for uncertainty, higher resolution predictions are not considered for real-time systems, and high computational infrastructures are needed. So that's why we need a digital twin Earth of the coast, a data-driven digital representation of the coastal dynamics that uses state-of-art physics-informed machine learning techniques and learn from the physics-based numerical simulations. Predictions with the COAST digital twin are orders of magnitude faster than traditional methods. That will allow real-time predictions for a range of atmospheric and climate conditions and probabilistic simulations to evaluate risk and support emergency management and decision-making. On top of that, the models can be made location transferable, and there will be no need for supercomputers infrastructures. This makes these models accessible to other countries, some of which may not have been able to afford a dedicated flood prediction effort. We build a digital twin of the coast by predicting the sea surface height either at current time or 30 or 60 minutes into the future. We do this by summarizing the bathymetry and the forcings, wind speed and sea level pressure, at the current time and up to 15 minutes in the past, in 5 minutes intervals, as multi-channels image. We are using this as input to our physics-informed computer vision model. The sea surface height itself is hard to measure and it's not provided as an input to the model. Now I will pass to Pisha that will talk about the results that we achieved.
Thanks, Helga. So here are our results in developing a surrogate model for Nemo Ocean using Fourier neural operator, which is a physics-informed deep neural net that leverages Fourier transform as a low-pass filter to learn the dynamics in the frequency domain. We use UNet, a deep learning model using convolutional neural net as the baseline for comparison. From the left to right are the animations of the Nemo simulation, FNO, and UNet emulation for present estimation on sea surface height. As we can observe from the animation, FNO generally reproduces the true dynamics, particularly for the trend of sea surface height over time. By comparing FNO and UNet using skew metrics, a mean square error, and structural similarity index, we found that FNO outperforms the baseline UNet. Also, note that using FNO, we can achieve hundreds of simulations in the order of minutes, which is magnitude faster than the physical model. Now passing to the results of the present and future estimation using historical dynamics up to the previous 15 minutes with mean square error plot shown on the right. First, FNO, which is the orange line, outperformed UNet, which is the blue line, for all the cases in predicting the current time step in the next 30 and 60 minutes. Further, we also observed an increase of mean square error over future time for FNO, indicating a potential divergence phenomenon when the predicting time step gets larger, which is still reasonable in this case, given that the mean square error is much slower than the UNet baseline benchmark. Also, note that the results were achieved with only a single run because of the limitation in time. With that said, more improvements can be achieved in the future. Now I will pass to Nis to talk about our platform and future work.
Thanks, Pirshi. Now that we have created the first digital twin to improve flood predictions, we want to empower others to do the same. The main contribution of our work at FDL is that we have built a platform to enable the development of machine learning associated surrogate models called coastal twins. It provides an extensible way to integrate simulations from physical models, such as NEMO and Cosmos, with machine learning models to produce reliable, accelerated emulation of coastal ecosystems. In addition to the tasks specific to this project, this platform will further foster collaboration between machine learning and earth scientists, speed up progress in coastal surrogate modeling, and be adaptable to similar surrogate modeling tasks. We achieved a lot during the last weeks, and we're already planning the next steps. First, after doing more thorough experimentation on NEMO, we will run our surrogate model on other physical models describing different regions of the world. Cosmos, for example, is a high-resolution, multi-scale model on the US West Coast that would hugely benefit from a surrogate model. Here, we can train on one geospatial location and apply this model to another location of the world, disentangling the physical dynamics from the concrete geospatial location. Secondly, we see our work on the frontier of a research domain which is currently dominated by solving differential equations numerically or shallow neural networks on the machine learning side. As far as we know, we are the first to develop cutting-edge physics-infused machine learning techniques to complex, real-world coastal systems. And it is important to continue extending our portfolio with more machine learning models, pushing both machine learning and earth science communities. With our current code base, we have laid the groundwork for interesting, valuable applications, such as uncertainty estimation, where the likelihood of certain outcomes of the simulation can be inferred. These and other improvements we will continue with research partners and deploy to the open source repository very soon. As confirmed by the latest IPCC report, ongoing climate change will result in more flooding and droughts. While our project does not prevent climate change, it helps to adapt to a world with more severe climate events. Currently, high-precision physical models are too slow to run in real time. In the future, with digital twins, precise, uncertainty-aware, life-saving flood prediction will be commonplace. So let's fight climate change and build on this work to improve flood predictions using machine learning.
Thank you very much, Digital Twin of the Coast team. Such important work. And I'm going to bring up Bill and our panel.
Wonderful. Thank you, Sarah, and thank you, team. Fantastic work. And of course, it couldn't be more timely together with the other two Earth Science projects done by this year's FDL teams. So joining Scott and I to talk about this work is Dava Newman, who is a professor of aeronautics and director of the MIT Media Lab. Also, previously during the Obama administration, was the deputy director at NASA, and most importantly, is an incredible member of the Board of Trustees here at the SETI Institute. So welcome, Dava. Thanks for joining us. And let's start with you.
My pleasure.
Can
you hear me?
Yes, we can hear you. What were your what are your reactions to what the team did and the promise that this kind of work holds for the future in terms of flood and other, natural disaster predictions related to climate change?
So congratulations, team. That was amazing. I have a whole list of questions. So first, I'll just give you kudos. I loved your talk. We'll get into the details, I'm sure, with some questions, but my hat's off because you went after the hardest question. And those are the kind of questions we like, to make the digital twin, and especially to really hit the physics. I'm biased, I am an aerospace engineer. So, and I love that you talked, about bridging the gap. That's what we find in our work. Of course, we have, amazing climate scientists. We have amazing ML, AI folks, but the whole goal is to get you all working together. And it looks like, this team is a big success. So my hats off to you. I do, again, have questions. This is really important work. So my questions are kind of future thinking too, about what do we do next? You mentioned other models that you think it'd be applicable to right away, because I would actually love to see this scale, right? As soon as possible, or continue working with this team, whoever wants to. It's just such an important contribution to get these physics informed. And I do have some questions on your Fourier analysis as well, but I'll leave it there, Bill, and take maybe some of my technical points offline and let us go around the squares here so we can all have time to talk to this incredible team.
Great. All right. Scott, your takeaways here. I mean, to what extent do you see this kind of work of digital twin being applied to not only things like coastal inundation issues, but all the other issues we're seeing related to climate change in terms of drought and fire, extreme weather events, et cetera? I mean, what's the potential here?
Well, I think, Bill, I'm really encouraged by this result. I mean, we've for years have been working on AI. We want to use it as a tool of science. And what we're finding now is that we're with projects like this, we're starting to see, and you're really working through, how do you actually use AI in science? And it's in the sense of, by making these predictions, you can sort of do a low res, scan across a much broader area. And then the AI makes a prediction. And like some of the other friends at NASA treat AI as an idiot savant, saying, I don't know what's going on, but there's something interesting here. And now that becomes the hypothesis for the scientific method. I think that idea of iterating between AI and science and these, what you call a digital twin, is the future of science in my heart. But it takes folks and leaders like you to actually show us the way. How does this actually work? And how does it validate? And how do you answer Dava's questions? That's what I want to know. Right? And as you go through that, because I think this, to me, is, you really push the forefront to me of science. like we did recently, the protein folding and understanding how proteins, in DeepMind. This is advancing in a very important area that matters for everybody on the planet. So thank you very much for your work. It's fantastic.
Yeah, wonderful. Deva, just before we jump to the next team, what are your thoughts? I know you have lots of questions that we'll have to work with you offline with the team to address, but what is a quick thought on your part of what you'd like to see next? What's the next stage of development in the work that the team that did this year from your perspective?
Thanks so much, Bill. So I'd say, the generalizing it and to capture other models, use the IBM's NeMo, that's great. But, the trap is everyone says it's only good for that one model. Show me how you mentioned, if it's generalizable to this model, because you want to ingest and work with the existing climate models. And then you decide, this is how I can show you how I've really sped up my calculations, because that's what people care about when they're in harm's way. We're in a flood or fire. We have minutes. Yes. Not even hours to get people out of harm's way. So if we could generalize it to using a little bit more in terms of different models, you would convince people. That's what I want you to. I want you to convince the world, not just me, that we can do this. This is generalizable, and those use cases are really important. So maybe a few more climate models, making sure that the uncertainty. I know we don't have much time, but the uncertainty analysis is key. So you've done great, but that's a really hard problem, and you're at the forefront. So the other thing is I want to see you all publish this because that's what you should do.
Yeah, absolutely. Well, it's certainly about speed, about better predictions, and about more time and more reliable predictions. So that's fantastic. Thank you, Deva and Scott, once again. And we're going to stay on the theme of extreme weather events and talk now to the team that, in spite of all the teams doing amazing work, this team I've always said had the coolest title. This is the Lightning team. So this team, work is on the geostationary lightning mapper instrument upgrade. So this is all about improving our understanding of lightning as a precursor and predictor of extreme weather events. And I think, Sarah, once again, we have an introductory video to launch this team's results.
Yeah, let's play the video from Aaron at NASA headquarters.
At NASA, machine learning is becoming a new tool for atmospheric scientists to understand processes of oncoming severe weather. In FDL 2020, our researchers showed how the jump signature of lightning flashes detected from space can be excellent predictors of oncoming severe weather events, such as tornadoes and hail. NOAA's Geostationary Operational Environmental Satellite, or GOES, has a camera called the Geostationary Lightning Mapper, which captures and records the intensity of light above a certain threshold, which is classified as lightning. But some lightning is lost. So we asked the question, can we achieve a greater classification accuracy of true lightning events by applying machine learning? I'm pleased to introduce the result, the Geostationary Lightning Mapper instrument upgrade.
And Lightning team, you're good to go.
Hello, everyone. We're the Lightning team. My name is Emmanuel, and thank you all for joining us. We're electrified to have you here. Without further ado, let's get right into it. So extreme events have affected mankind since the dawn of time. For example, tornadoes are one of the most deadly and hard to predict storms in the USA. Wildfires are frequently occurring events which destroy acres of our precious forests and wildlife therein. One key component that each of these phenomena share is that increased lightning activity can be used to predict the onset of these extreme events. So our goal is to improve our ability to detect lightning early in the development of a severe weather event and to provide timely warnings to save the lives of affected residents. We now have the technology to pick up on these lightning events even from space. The Geostationary Lightning Mapper camera, in particular, is specifically designed to measure photons reflected from the Earth. And thanks to these innovations, we now have more coverage of events, more frequency of events, and a lot of data. So this is what the sensor actually sees, including the strobing. Yeah, that's real. Shocking, I know. What we see here is a time lapse over the course of a day, whereby each frame represents 1 hour. And as you can see, there are a lot of activated pixels, which may or may not be lightning. On a more granular level, this is even more difficult. The graphic to the right shows us what we actually see under the hood without being grounded in the context of the Earth. As you can see, it's extremely difficult to tell which of these points in a 3D space correspond to lightning events. And at this point, even domain experts have difficulty distinguishing between activated pixels that are lightning and those that are noise. So this leads us to our scientific question. Can we use machine learning to find patterns in the data that help us identify lightning? And now my colleague Satyarth will walk us through some of the aspects of machine learning.
Thank you, Emmanuel. To answer that question, honestly, we don't know. But looking at the data, we think we can do something. And hopefully by the end of the presentation, we will have a better answer for you. So here's what we have. A really messy, noisy data on the left that doesn't seem to make any sense. And the output of the current filtering system on the right, which is majorly based on scientific thresholds. Although it seems to be less noisy, it still doesn't help us pinpoint what is lightning and what is not. What we aim to do is to leverage the benefits of machine learning to maybe find some hidden patterns that are not directly evident. So here's a pipeline that addresses this problem. Because our sparse dataset is so huge, we define a format to crunch all this information. This module in our pipeline is called the data processing module. Getting into a little more detail, we take our huge raw data, tile it up across space and time to create smaller patches, and compress each patch across time to reduce the size of the data. The diagram on the right shows the magnified version of a single patch with a spatial dimension of 32 pixels plus 32 pixels, which corresponds to an area almost as big as the size of the state of Colorado. Across time, we create each patch to contain information for half a second. The blob in the plot is a potential candidate for being a lightning event. This plot on the right shows the temporally compressed version of the patch. This helps the data become a little less sparse and a little easier to explore and interpret. Next, I'll ask Julia to explain the further modules.
Yep, thanks, Satyarth. So after the data has been processed, we can proceed with the next step in the pipeline that consists of dimensionality reduction. This means that we want to reduce or compress the information which is encoded in our data. A standard technique for dimensionality reduction is to use an autoencoder. This means that we take a 2D image that we have created before from the raw data, we feed it into a neural network, and we obtain a representation of this image that lives in a smaller dimensional space. After applying this process to our whole dataset, we obtain an entire set of representations that capture the main features of the original images. And then we use these representations for the final part of the pipeline that performs clustering to discover groups of similar examples within our data. So we take the lower representations that we found before, we cluster them, and in our setting, ultimately the ideal goal is that images that contain lightning and images that contain noise will be assigned to separate clusters. So let's have a look to some images from the green cluster. So we notice that we are indeed capturing some similarity of the images here, but this similarity seems to be heavily influenced by the position of the signal in the images. For example, this cluster contains images where a signal is in the bottom right corner, and this other cluster images where a signal is in the bottom left. And this is an issue because the position is not really informative of whether the image contains lightning or not. What is more informative is actually the shape of the signal. And here I'll ask Emma to explain how we address this issue.
Thank you, Julia. One way to focus on the shape of the data instead of its position is to change the way it's represented to our algorithm. Specifically, we represented the data as a graph instead of as an image. This is a plot of 8,000 sample patches after they've been represented as graphs. You can see that the points form tighter groupings than we obtained previously with the image autoencoder. Looking at some example points from cluster 1, we can see that the patches contain small pairs of points that have a similar structure, but different locations in the image. This is good because it means that our model can now focus on the shape of the data and not its position. And if we look at points from cluster 2, they also have similar shapes but different positions, as desired. Given these results, we plan to continue to use this graph-based approach in our future work. In addition to testing the graph-based representation, we also experimented with a different metric, the Gromov-Wasserstein distance, which is blind with respect to position and focused on the shape of the signal. We found that when we used the Gromov-Wasserstein distance on raw data, we were able to successfully group together images that had very similar shapes. This is promising, and we propose that this is also a useful metric to use in our future work. In closing, our team has been asked if it's possible to use machine learning to find patterns in the data that can help to identify lightning. We have found that yes, there is structure that we can exploit. We discovered that standard methods are focused on the position of the data within an image, which is not desirable. But we found that graph-based representations and the Gromov-Wasserstein distance lead to better clustering results. Overall, we applied machine learning to identify lightning structures in data sets from satellites. This work will enable us to find crucial lightning events to assist in the timely detection of severe weather. These results will contribute to protecting people and property from tornadoes and wildfires throughout the Western Hemisphere. Before we leave, we'd like to say thank you to the entire Lightning team who made all of this possible. Thank you also to our sponsors for their support, especially Lockheed Martin, Microsoft, NASA, and FDL. And finally, many thanks to you, our electrifying audience, for listening.
Thank you so much, Team Lightning. That was really fantastic and really relevant as I live in a place that has many severe weather events. So I'm very excited about what you're doing. And I'll go ahead and bring up Bill and our awesome panel.
Wonderful. Thanks, Sarah. And I feel like a charged particle now. Great job. So I think it's clear that this team demonstrated the ability to more accurately characterize and identify lightning events and distinguish them from other phenomena, which can be an important contributor to improved severe weather events. So joining us for this panel, joining Scott and I for talking about this is Samantha Eddington, who's a systems architect at Lockheed Martin. So Samantha, what's your takeaway here on the science side in terms of, I think the team demonstrated an improved ability to characterize lightning. Can it help us really give better warning and better prediction to extreme events in weather?
Yes, so it's really exciting results because I mean the GLM instrument that they talk about has been on orbit gathering data for almost 5 years now, and still we are able to possibly upgrade its performance, even though we can't go up and change any of the hardware. So that's really exciting. And if we can do a better job creating the final lightning data product that is seen by the forecasters and atmospheric electricity researchers, then that can really improve their ability to predict as the severe weather that the team was talking about earlier, the tornadoes and predict the wildfires, which is very exciting for me in California, which is currently on fire. So I'm really excited about that. And you also got to see kind of the raw data, which most people don't see for instruments like any instrument that you would go and look at data that you might see on the news or online. It's going to be processed, and there's a lot of processing that happens behind the scenes before you see these images or the data. And so you could see from this presentation just how much processing we have to do on the ground because we want to get all of the lightning data on the ground so that we can see as much of it as possible. So a lot of noise comes with that, and you have to filter it out on the ground. And seeing some of the machine learning techniques and how they might be able to help us do that is very exciting.
Well, it's amazing because you raise an absolutely important point here. This is not just about advanced or improved data and analytics. It really is about sort of synthesizing an actual upgrade to an instrument, to your point, without actually physically visiting the instrument. And I think the implications for that are profound. Scott, what's your takeaway in terms of methodology and approach on the machine learning work that was done here and its broader application?
Well, first, just holy cow. I mean, just if you look at I saw the raw data, Samantha. I don't know how in the world you find lightning from that. It just looks like a mess. That was amazing. That's incredible. That's just the holy cow effect. But what's interesting, if you look at the team, is you looked at autoencoders and whatnot, and you look at things spatial, and you on your own said, we need a better representation. These image nets and CNNs aren't going to cut it. And you went for graph networks. I don't know if you read Jeff Hawkins' book yet on 1,000 Brains Theory, but he has this conjecture that what we learn in the cortical columns in our brains and our neocortex is a reference frame. And we have some of the winners of the Turing Prize are now thinking about, capsule networks, where you actually try to learn the reference frame of what you're seeing. And that is much better than actually trying to just do it with a CNN. So I think you're onto something here. And I would really love, afterwards, connect me to LinkedIn. I'd love to know your thoughts about what Jeff's thinking and how can you advance the field of AI? Because he's thinking that sort of is going to open up the whole new area, Bill, in artificial intelligence, to go after the holy cow effect of taking this jumble of data points and saying that's lightning. That's just incredible.
Yeah, fantastic. Well, that's awesome. Well, thank you very much to our panel for those comments, and thanks to the team and a wonderful job. And again, as the team already did acknowledge, I want to once again acknowledge our partners on that team, which were Lockheed Martin, of course, and NASA Earth Science within the Science Mission Directorate, and Microsoft, who helped support the compute for that incredible work. So we're now going to go from Earth to the sun and make a big leap here as we move into our next team presentation. And they're going to talk to us about solar drag. This is about understanding the impact of solar dynamics on the Earth's thermosphere to better characterize the effects of atmospheric drag on spacecraft and satellites in Earth orbit. And the partners for this project include the University Corporation for Atmospheric Research, or UCAR, NASA Science Mission Director Heliophysics, and Google Cloud once again. So with that, I think, Sarah, we have a partner video and then the team launch video to take us into the next talk.
Yeah, and we can go ahead and play those videos, and Lika will introduce the challenge.
Great.
The sun gives us life. Without the sun, life on this planet would not be possible. We spent so much time looking really far into the universe, but our own star, the sun, is right there, and there's so many things that we don't understand about it. The sun is incredibly dynamic, and there's a number of processes that go on the surface. And some of them can lead to particles being ejected into space. And when these particles travel to us, they can interfere with communication systems, with GPS systems. They can destroy our satellites and our power grids, which means we're going to be sitting in the dark. What my team is trying to do is, we have images of the magnetic field of the sun for the past 50 years. The images that we have from back in the day are significantly lower resolution than the images that we capture today. And we're trying to use machine learning to increase the resolution and make them higher quality, to understand how we might be able to tie that in with effects that we're seeing here on Earth. Millions of images that we're sending through a network that we're trying to get something useful out of. Without Google Cloud and Intel CPUs, none of this would have really been possible, because we wouldn't have had the computing power, and we probably would have waited for a whole year for our models to train. But instead, with one click of a button, it takes us 5 minutes, and then our model is done. In a world where we're so reliant on satellites for communication systems, but also we need to understand exactly what makes us vulnerable. I really hope that in the future, scientists will make more use of machine learning to have computer scientists and natural scientists working together on solving the world's biggest problems.
Just like our home atmosphere is subject to violent and damaging storms, such as Sandy, Our space environment undergoes violent disruptions driven by powerful flares and coronal mass ejections from the sun. These storms, which define the weather of our space environment, are much more energetic than the storms of terrestrial weather. And the boundary of the Earth's atmosphere and space is in constant flux. Not surprisingly, it is our sun that has the biggest external effect on our atmosphere. Our planet and our star are in a continuous dance. Any object in low Earth orbit, whether it is a deorbiting spacecraft or the International Space Station, will have variations in its trajectories as it interacts with the thermosphere. The main reason for these changes in trajectories is atmospheric drag, changing in response to the activities on the sun. We asked, can we use synthetic machine learning data to improve the modeling of the atmospheric drag? Any improvement on predictions of spacecraft location, likelihood of collision, re-entry prediction, and communication would be of great benefit to the space situational awareness community. Therefore, I am really excited to introduce the work of this team. Solar drag, or really atmospheric drag.
Hello, everyone. Thank you for taking some time off from your schedule to hear our presentation. We are the Solar Drag team. I'm Stefano. I'm the second member of this team. And over these 9 weeks, I worked together with Bernard, with Edward and Jorge, and supported by the 3 amazing faculty members that we had, Giacomo, Gunes, and Chris, supported by 2 research advisors, Mori Baja and Eric Sutton. Our challenge is associated extremely with the sort of all of the parts associated with the sun. In particular, we know that for what concerns the lower part of our atmosphere, the population of satellites is continuously growing in time. That is often a problem, especially like the more we go on in the future, the more it will become a problem, because whenever 2 satellites actually intersect their trajectories, they can collide. Whenever they collide, they actually can generate a cloud of debris. This particular cloud of debris is important that we must have to not happen in the future. So in this case, when we form this cloud of debris, we can extremely endanger future accessibility and safety in space, especially for the lower part of the atmosphere, what we refer to as the thermosphere. But what is the main driving factor of all of those satellites and objects orbiting around the Earth? Of course, mainly is the Earth, it's gravitational pull of the Earth. But the secondary force is a perturbative force known as orbital drag. In this case, the orbital drag is associated with the interaction of the spacecraft or those objects orbiting the thermosphere with all of the particles of the thermosphere itself. It is important, especially to characterize the thermosphere, especially the density, so we can estimate this particular perturbative force, again, the orbital drag. Because whenever we improve the estimation for that particular force, we can then improve how we locate, how we estimate the location of all of these objects, so we can prevent those collisions to happen. The most important challenging part of this particular thing is that the thermosphere and the atmosphere reacts with respect to how the sun emits all of the energy, and all of that particular solar activity interacts with the atmosphere, all of the amount of energy that arrives to the atmosphere, and in this case, to the thermosphere itself. But modeling this particular interaction is extremely complex. So here it is, the challenge that we tackle in our team for the solar drag for this 9 weeks FDL challenge. In particular, we translated this challenge into a question, our research question, which is how can we use machine learning, so a data-driven approach, having all of this information from the sun, arriving from solar indices, as well as image from the sun, ingest all of this information in a machine learning model that we can learn, we can train such that we can improve our estimation for the orbit drag. And this, I'll hand it over to Edward, which will be introducing to you the first part of the results that we achieved in this 9 weeks effort.
Thanks, Stefano. So the sun emits light and energy that's absorbed in the thermosphere. And in order to estimate the thermospheric density, there's a lot of different data sources that we might use. So in terms of solar imaging, there's images from the Solar Dynamics Observatory, but there's also irradiance data, geomagnetic indices, and things like that. So we want to use these disparate data sources into a machine learning model and estimate the density, as well as outputting uncertainties. So what do our different machine learning pipelines look like? So there are two separate pipelines. So the first on the left is the space weather indices forecasting. So space weather indices are numbers that are used in thermospheric models. So being able to forecast these indices is very important to working out where your spacecraft is going to be, because it tells you how much drag it's going to encounter. So in yellow, we have the different inputs to our model. In blue, we have an ensemble model, which just means lots of different models, which we train together to produce a range of values, which is our uncertainty. And in the red, we have the output. And when we say loss, we just mean how wrong is our model. And that's what we want to reduce. And similarly, for thermospheric density modeling, we have a whole range of different data sources that we'll put into a neural network and be able to output the loss as well as uncertainties in our outputs. But crucially, we really wanted to focus on creating uncertainties in these outputs because it's not often done in space weather forecasting. So I mentioned solar features. What exactly do I mean by that? So here's an artist's impression of the Solar Dynamics Observatory. Now, the Solar Dynamics Observatory has been running since, I think, 2010, and it's been taking images of the sun in 12 channels every 6 minutes in high resolution. So what do I mean by channels? So by channels, I mean like a normal image normally has actually 3 images behind it, red, green, and blue. Now, for the Solar Dynamics Observatory, it's actually taking in 12 channels, and there's the top, as you can see here, there's the top 3, the sort of strange looking ones in the top left are the magnetic field strength on the sun. And the remaining 9 are extreme ultraviolet channels, and they all contain different information from each other. So the idea is to condense these different channels through a feature extractor. And from these, and features just means expressive things about the sun. And we use these extracted features for a downstream task. So I'll pass you over to Bernard, who will talk about forecasting these space weather indices and also how we use these images.
Thanks, Ed. I will now talk about our space weather indices forecasting work. The top left figure shows our simplified ML pipeline for the space weather indices forecasting. We pass as inputs the solar proxies or solar radial flux proxies and the geomagnetic indices to our ensemble of LSTM model, and then produce the loss and the uncertainties in predictions. We generate a simultaneous multivariate forecast of the solar radial flux and the geomagnetic indices using this process. The sun has an average of 27-day rotation period, and so we use as input 4 solar rotations worth of input data to produce 1 solar rotation worth of output data, that is 27 days. The figure on the bottom left shows our model's performance at the root mean square metric against other simple baselines. The figure then on the right is a sample forecast showing the dotted lines represent the ground truth, the solid lines represent the mean of our ensemble prediction model, and the shaded regions show our uncertainties. Now moving on. On this pipeline, we add the solar image features from the feature extractor to our ensemble model as inputs. So along with the solar proxies and the geomagnetic indices, we're adding the solar image features from the feature extractor to produce our results. And on the bar chart on the right, you can see for the solar indices, there's a 30 to 40% improvement at the R root mean square metric for the solar indices. This shows us that adding solar images as features improves the performance of space weather indices forecasting. And with this, I pass on to Jorge, who will talk about the thermospheric density work.
Thank you, Bernard. So we will now look at our model for the density in the thermosphere.
So the thermosphere corresponds to a region in the atmosphere where satellites in low Earth orbit move, and its density determines the strength of the drag on the satellite's motion. So essentially, we're using data from high-calibrated satellites together with solar and geomagnetic activity data to predict the thermospheric density. So how do our results actually look like? So in the top plot, we see the thermospheric density as a function of time. The blue line represents the satellite ground truth data that we're trying to predict. The red line represents our actual prediction, and the shaded region is the uncertainty in our prediction. On the other hand, the yellow and black lines correspond to predictions from state-of-the-art empirical models. And what we see is that our model is able to accurately reproduce the thermospheric density values from the ground truth data. Now, in the middle and bottom plots, we show error metrics for prediction. Those plots show that our model is doing a pretty good job in predicting the thermospheric density. And next, we ask, how does the reconstruction of the global thermospheric density field actually look like? So on the left, we see the thermospheric density field reconstruction from our model. And on the right, we see the thermospheric density field from a state-of-the-art empirical model. And we see that our model is indeed able to reproduce the structure in the thermospheric density field. So being able to tame the thermospheric dragon. So with all these exciting results, we can now try to summarize our results so far. So we've been able to produce some space weather indices forecasting, and we also produced a thermospheric density modeling. We have provided uncertainty in our predictions, and we have been combining multiple data sources. And with this improved forecast and drag estimation, we're in a place to provide more precise orbit estimation for spacecraft, as well as for assets that are important for space agencies. So we would like to thank NASA, Google Cloud, UCAR, and all of our partners. We would also like to give special thanks to all the researchers that gave us incredible feedback and support. And finally, we would like to give a huge thanks to our awesome faculty, Gunesh, Giacomo, and Chris. Thank you all for all your support and hard work. And thank you very much for listening.
Well done, Solar Drag team. And we'll go ahead and bring up our panel and Bill to host our Y panel.
Great. Well, that was really amazing. And I have to say, I don't think I'm really overstating it here. You had sort of two challenges going on at the same time, where you had two different problems converging. One was developing this improved predictive modeling of the sun's behavior, but the other understanding its impact on on thermospheric density, and then ultimately that helps us with more accurate predictions and understanding of spacecraft and satellite orbits. So joining us, Scott and I, to help unpack what this team achieved is Mark Chung, who is a senior staff physicist at Lockheed Martin. And like Scott and many others here today, Mark has been working with and supporting the FDL program now for many years. So Mark, thanks for coming along and joining us, and tell us your perspective of what's been achieved here.
Thanks, Bill. Hi, everyone. So first of all, I would like to congratulate the team for the astounding productivity that you had in a short amount of time during the summer. You had a set of very impressive results that unfortunately, because of time constraints, you couldn't go into detail. And I have so many questions in my mind. I'm sure we will catch up offline. But I want to frame the type of work and the importance of your work for our audience here. Imagine if you're going out on a boat trip and you didn't know how to predict the tides. That is sort of what's going on right now when we send our satellites up into space. We're not very good at predicting the atmospheric density in the high atmosphere, and to predict what sort of atmospheric drag our satellites would experience. And then we decide, okay, let's send fleets of thousands, hundreds and thousands of our ships into space, still without knowing how to predict the tide. So this is why it's so important for us to be able to do so. And in the past, people have been using a so-called F10.7, this radio proxy, because that was what was available. But since Solar Dynamics Observatory and continuing on with the SUVI instruments on the NOAA GOES satellites, we're going to have decades-long observations of the extreme ultraviolet output of the sun, which is driving the changes in the thermospheric density. The model that you apply here, the models you have trained here is not only relevant for the near future, it could have potentially an impact over the next decades. It really could change the next generation of how we do modeling and predictions of atmospheric drag. So I applaud you for taking on this big task and having such a good results.
Thank you, Mark. I couldn't agree with you more. Scott, so we're seeing a consistent theme here in terms of AI and ML tools helping us not only better understand and characterize phenomena, but also develop these predictive models of what's going to happen in the future. Where do you see this kind of work going of the sort that the solar drag team did?
Well, I don't know why we don't have space weather. I mean, we need Mars weather, Titan weather, and the journey. And we don't venture out, as you said, Mark, into the seas until we know what's going on, right? Same thing for flying. And I think that's just going to be normal in the next decade or two, right? As you're venturing out as a human race. And this is just magical to me, Bill, because we take these enormous cloud compute, and that is just a tool for these individuals. And what they're working on is something I see in everyday business, which is sensor fusion. Because what's interesting is these highly complex models we put together can fuse multiple different things that we struggle as humans to understand, and then produce conjectures that we can then go test through a scientific method. I think that is also a hallmark of what we're seeing with AI. And it's just, hats off to the team. Fantastic result. I love how you sort of show the magic of a cloud applied to science. And I'm just learning from you. So great work. Thank you.
Well, it's interesting what you say, Scott, because it's like we try to, break things down when we understand them. In understanding them, we're trying to predict what's happening next. What are sort of primary influences and secondary and then tertiary. And what you're saying, if I'm understanding you correctly, is that AI and ML have the opportunity and the ability to synthesize all of these at once, the major effects, the subtle effects, and understand how they interact instead of, deconstructing them the way we tend to because of our limited capabilities. So really fantastic. All right, so we're going to stay with the sun, our very own star, in addressing the last teams, but by certainly not the least team's work in this year's FDL research program. So the last team today that you're going to hear from is going to talk about the solar wind. And it's about uncovering the origin of solar wind using machine learning to better understand the structure and nature of the solar wind and its impact on Earth. And our partners for this program include, once again, NASA SMD Heliophysics, and of course, Google Cloud. And I think once again, we have a video to introduce the topic. Sarah?
Yes, we have a video from Lika introducing us to our next challenge, so we can roll that tape.
Many stars have an extended atmosphere that reaches out beyond the planets into their interplanetary space. This atmosphere is made of charged particles that continuously flow outwards in a spiral. This is the solar wind that travels towards the Earth, where it runs into the atmosphere, our atmosphere. As the protons and electrons from the solar wind hit particles in the Earth's atmosphere, they release energy and creates aspects of space weather conditions. Understanding the structures that make up the solar wind, such as in the magnetic field, velocity, temperature, and density, is essential to understanding and predicting the behavior that impacts us here on Earth. In this challenge, we invited the team to use the machine learning to detect solar wind structures, comparing measurements close to the sun from the new Parker Solar Probe mission, as well as other missions far from the sun. This allows us to study how patterns in the solar wind develop as they propagate further out into space as they leave the sun. We are also proud that this team is hosting 2 undergraduate students as research interns. This is part of a larger effort to extend Frontier Development Lab's reach and support researchers from currently underrepresented groups in physics and machine learning research. I'm delighted to introduce this team's work here today, uncovering the origin of solar wind.
Hi, everyone. Thank you so much for sticking with us through all of these amazing presentations and discussions. On behalf of the Solar Wind Evolution team, we're all very excited to share with you what we've been up to this summer. My name's Amanda Camarada, and I am joined by our amazing researchers, Sudeshna, Nathan, Mavis, Hala, and Marcella. But we also want to give special thanks to our mentors, Anna, Andres, Cyram, Adam, and Anthony, for all of their knowledge and support this summer. So let's begin with what the solar wind is. The solar wind is a constant ejection of charged particles expelled radially from the sun's corona. On this top-down view of our solar system, you can see that as the sun rotates, the solar wind creates this ballerina skirt effect that extends outward into space. The different colors denote different densities, with the lighter colors corresponding to higher densities. So you'll see that the solar wind does not travel outward in a uniform structure. Now, our Earth exists in a constant bombardment of the solar wind. And while we are largely protected from the solar wind by our magnetosphere, the solar wind can affect the technology in space that directly impacts our way of life, such as communications, GPS, and long-duration missions in space. Sudeshna will tell us more about why the solar wind is important.
Thanks, Amanda. So, the solar wind is one of the key drivers of planetary atmospheric loss. So what we see on the left here on the illustration is the bombardment of solar wind particles on Earth. But because we have a global magnetic field, a majority of these particles get deflected. But if you're Mars, you're not that lucky. Because Mars doesn't have a global magnetic field, the solar wind can strip away a large chunk of the planet's atmosphere. So this brings us to the point that if we want to have a good understanding of how a habitable atmosphere develops and survives around the planet or even exoplanet, we need to know about the solar wind, its origin and its evolution through space. That's why this summer at FDL, our team investigated the different structures embedded in the solar wind and as it propagates throughout the space. So that's why Nathan is going to talk to us about the different structures and what we did today, this summer.
Thanks, Sudeshna. So embedded in the solar wind is the interplanetary magnetic field. And now, just like how the wind blows past you on a breezy day here on Earth, the interplanetary magnetic field blows past our instruments in space as it is carried outward by the solar wind. In measuring the magnetic field, we can observe structures like we see here on the left. This structure is known as an interplanetary coronal mass ejection, and they occur at a rate of about 10 to 50 times per year, depending on solar activity. As the largest structures embedded in the solar wind, they are easily identifiable in instruments, and they were discovered relatively early on in our journey to understand the solar wind. Next, we have interplanetary magnetic field enhancements, which occur at a rate of about 10 to 20 times per year, but they span significantly shorter durations of time, on the timescales of about an hour or two. And they're much smaller in amplitude, leading to a delay in their discovery until the 1980s. Now, if we go even smaller, we have switchbacks, which have extremely high occurrence rates of order 5,000 per year. Now, interestingly enough, these objects went undetected in the slow solar wind until 2019 because they exist in a region of space that was previously unexplored until the launch of the Parker Solar Probe in 2018. So this begs the question, what other structures are out there that have yet to be identified? And how do we look for them in the vast amount of data that we have available? So just how much data is there? Well, there's a lot. And here we are showing 205 5-minute intervals that add up to just 17 hours worth of observations. And you can already see how overwhelming it would be for a single person to sort and catalog these structures. And that 17 hours, well, that's just 0.1% of our full data set containing nearly 15 hours worth of observations. But this isn't just overwhelming for a person, it's also overwhelming for a computer. Traditional approaches require pointwise comparisons between two different time series, which is computationally expensive, requiring over 90 trillion operations. And this is largely infeasible for our accelerated 8-week timeline. So instead, we used a non-traditional approach, to be explained by Mavis, that significantly reduces the number of computations by a factor of 30 million in order to sort and understand our structures in the solar wind.
Thanks for the rundown, Nathan. Now let's take a look at how this non-traditional approach works. On the left, we have a collection of time series data that we want to store. First, we divide our time series data into different levels. So here you can see that we have level 0 and 1. Next, we split our time series data into smaller segments and assign each segment a letter. And then finally, last but not least, we represent the data set as a word. All these data sets are very similar and hence have the same word sequence, A, B. Our machine learning approach goes through every magnetic curve in our data set and represents it as a word sequence. If there are magnetic curves that have the same word sequence, then our method will group them together into a single batch. As a result, we can group together all the similar patterns without doing any tedious calculations, as Nathan had mentioned. Once the machine learning algorithm is finished, we can look through all the results to see whether there are any new structures that occur frequently enough to be considered important patterns. Marcella will be showing this next.
So now that we have our data, which are time series with 5 hours interval each, we sort them and split into 5-minute time segments and convert them into the word sequences that Mavis just said about. After that, we embed it into our pipeline to be clustered according to their patterns. This figures shows all the patterns inside a 6-hour interval at the left. Each color represents a different pattern. On the right side, we highlighted the 4 most frequent patterns from the specific example of September. We see that the data has the same color are grouped by similarity. It's important to note that now we can encode 90,000 segments using only 300 patterns. There is a reduction for human scientists by a factor of 300 times less patterns to analyze. Besides, in our pipeline, we can play with scales, applying different time chunk segments besides the 5 minutes, which can bring us different results. In the next slide, Hala will emphasize why our pipeline is a powerful tool for we scientists.
Thank you, Marcella. After our 8-week program, we are now able to identify distinctive features and group similar time series into recognizable patterns. Our findings revealed multiple clusters of solar magnetic structures like switchbacks, and most importantly, unique signatures which have been unclassified and understudied to this day. This paves the way for the comprehensive annotation of solar wind data, enabling the application of powerful machine learning techniques. Here, you see 1% of the 90,000 segments that we have so far sorted and grouped into 300 clusters. In this example, we have 8 clusters from the 300. Now, instead of having to stare at 90,000 segments, together with heliophysicists, we can interact with the reduced number of patterns to better understand the structure, evolution, and origin of the solar wind with an unprecedented level of detail. We thank the FDL, NASA, City Institute, Google Cloud for providing us with compute resourcing, our Intel mentors for their precious guidance, and all the generous partners without whom this work would not have been possible. Thank you for listening.
Thank you, Solar Wind team. That was very well done. And we'll go ahead and bring up our panel with Bill. And I just wanted to say, I think that it's amazing, these panels. We've gotten everything from analogies of solar tides to a book reading list from Scott. So I can't wait to hear what this last panel is going to say.
Absolutely true. Well, it's excellent. And I do want to say before we get into the panel, don't go away after the panel concludes our remarks, because we have more to come here, including some award presentations for the teams and their work this year. And we're going to hear also from the leadership at NASA Ames Research Center, who's been a partner in the FDL program from the beginning. So please stay on with us. as we continue the program. And with that, let me introduce another panelist joining me and Scott for this discussion on the solar wind, and that is Sairam Sundarasan, who's a deep learning research engineer at Intel. So hello, Sairam.
Hi, Bill. Hi, everyone. Excited to be here.
So you're working on deep learning techniques at Intel. From your point of view, what's the breakthrough work done by the team here in their approach to this problem set?
First of all, I want to congratulate the team for the immense amount of hard work they've put in over the summer. I know how much they have, they've worked really hard, and the results speak for themselves. From sort of the machine learning side, I think this project highlights one of the most important perspectives or the important components of machine learning, which is the data, because clearly this problem is a limited labeled data set, if you want to call it that. So you have almost decades worth of data and you don't have somebody to label it all for you, which makes it a very challenging problem from the machine learning side. So the fact that they were able to identify a structured method to holistically approach it, identify patterns, I mean, basically feed the data to the machine learning pipeline, allow it to find patterns itself versus sort of forcing human bias into the picture, allowing it to find structure, and then using those structures to work with scientists to sort of identify meaning. I think that's a sort of a funnel approach that really allows you to conduct research. And secondly, I think it allows others to stand upon the shoulders of sort of the folks who have built this pipeline to further the research forward. So from that perspective, I think it's very novel.
So that's a really interesting point, Sarah, because it seems like we often think of these AI and machine learning tools as these things we can take out of the toolbox and simply apply to a problem. But in this case, for example, the team had to do a lot of work with the data. I believe it was the team as opposed to an algorithm that went ahead and decided to structure the data sets into these quadrants that therefore allowed or facilitated the algorithm to function. Am I understanding that correctly, Scott? And is it, what's your sense on this notion of data preparation and or methodology and approach to ensure the success of an AI ML approach?
Yeah, I think Saram sort of nailed it. It's like a lot of times solving the problem is all about framing it correctly.
Yeah.
And I think and this is just a genius, guys. I mean, I see time series all the time, and what's really fascinating to me, Saram, is that as they get into this, you can look at a time series, and by human ingenuity and saying, you know what, we're going to do a 2D bandpass filter, and we're going to label the segments and then turn it into a grammar, much like you do nucleotides in DNA. And then can we analyze that as a pattern? That is just so flipping cool. And but then the next thing is I'm curious about that. Can you use sort of like semi-supervised learning to learn to learn that 2D segmentation? That'd be pretty cool. Then also, could these techniques be used in these other things like next generation sequencing, where now we can actually read the source code to life, but that basically turns nucleotides into speech waves, right? So I think you're really into something here in terms of your ingenious insight, and how does it apply to speech recognition, next generation sequencing, and other complex time series analysis, even Wall Street. So maybe Wall Street's going to call you next. Don't leave, stay in space.
That will fund FDL for the next decade. Let's
yeah, there you go. And so this team of the hedge fund, right? And we're done.
Yeah, exactly. Let's see if we can take that.
We'll tokenize the whole thing. Yeah.
And I want to explain for any of the uninitiated. So flippin' cool. That's a technical term.
That's very
Cloud.
technical, Bill.
Yeah,
that's
very technical. So
yeah.
You can Google that undoubtedly and sort of get a translation. But anyway, thanks, Scott, for those. Sarah, any closing thoughts from your perspective before we jump to the awards?
No, sorry, go
ahead. Did I hear it wrong?
Yeah, no,
I heard it wrong. Please go
Sarah
ahead.
and Sarah.
Okay, no, I was just going to say, like Scott said, I think mapping the problem correctly, like there's been immense advances done in machine learning, particularly in language understanding, language processing. So framing a time series problem as sort of this unknown language that the universe is speaking to us, and sort of mapping it into sort of a structure that machine learning can understand, and then categorize as elements of that grammar, and then analyzing that grammar with scientists. I think that's really so flipping cool, so to speak. So
Yeah, it's like
that's been the
reductionist
consensus
proof,
pretty much
right.
across the board. So
but you're right. So
congratulations to the team.
Are they getting to the language of the universe? It's a really interesting fundamental question over coffee, right?
Absolutely.
Really
So, I mean, it's been speaking to us for so many decades, and it's time for us to sort of understand what it's trying to say.
Absolutely. So, Sarah, I think we're going to have to talk to the leadership team at FDL and consider changing the name from FDL to SFC for So Flippin' Cool. But in any way, thank you very much, Sairam and Scott. Thank you for all your insights with every one of these presentations. And again, for the incredible and absolutely transformative assistance and support of Google Cloud for the FDL program. So with that, Sarah, let me turn it back over to you, because I guess we have some awards coming up and then some closing thoughts from NASA.
Yes, we definitely do. And I do think, Scott, we found our new slogan for our t-shirts next year. So thank you. And with that, we're going to go ahead and move on to our collaboration awards. So how this is going to work is we've invited all of the FDL team members to be able to come on board. And we're going to have Bill share with us each of the awards and what they mean. And I will announce the results. So Bill, would you like to go ahead and kick us off with the first award?
All right. So the first award, we try to recognize all the different and amazing contributions that the teams have made in their domains and their activities. And there's so many, but we've got some pretty interesting and fun awards that we've worked hard to evaluate what the teams have done and assign accordingly. So the first award is the most dramatic pivot. So pivoting, as you probably know, is an action taken when new opportunities arise unexpectedly. Sometimes this means starting completely from scratch after much commitment is put into one idea, but the most dramatic pivot award represents these changes in direction, at times unwanted, but certainly necessary. Sarah?
Great. And the award is going to go to our Solar Wind team. By pivoting to unsupervised machine learning and developing their ISACs implementation, SolarWind has changed the way future FDL challenges will interface with very large sets of unsupervised objects, and they're already finding interesting SolarWind patterns. And SolarWind has also created an environment where 2 undergraduates have flourished and been able to make significant contributions to this effort. So congratulations to the SolarWind team. I want to make sure that this team gets the applause and that we have them all spotlighted so that everyone is able to see them. So congratulations again for the most dramatic pivot award.
And by the way, we actually make these little trophies that you see here, and you will be getting these physical trophies sent to you, since we can't hand them to you in person this year, but that's very exciting. All right, next up. So next up is the most useful contribution. What defines a contribution? In machine learning, it's often hard to spot the thankless task of data preparation on behalf of the community, or the application of a freshly minted ML methodology to a new domain. In some instances, it's something that widens our perception of what is possible. The most useful contribution can be any and all of these things, as long as the beneficiary is for all of humankind. Sarah?
So the award goes to Astronaut Health for their wider impact on not only one domain, but on biological, medical, health science, and in addition, federated learning. The findings of CRISP and the capabilities in the platform have such a high potential and are already sought after by partners for integration and extension on several pathways. I can't emphasize enough how critical they're, and the team from last year, which is also here, thank you guys for joining us too, are to advance those domains. So congratulations to our Astronaut Health team. Well done.
Well done. Congratulations. And just so you know, by the way, this is just like the Academy Awards. I have no idea who the winners are. Sarah's got these envelopes that she tears open. I haven't seen them. They've been kept in a secret briefcase by some accounting firm in New York. I don't know, but it's all top secret. So congratulations, Astronaut Health. Next up, we have Unexpected Discovery. So Unexpected Discovery Award is just like dirty dishes helped the discovery of penicillin, and melting chocolate bars triggered the creation of the microwave. actually also an attempt to improve the hearing aid, invented the telephone. The Unexpected Discovery Award represents that ability to stumble upon a breakthrough. As Plato once said, science is nothing but perception. Sarah.
And the award goes to our solar drag team. The solar drag team for understanding forecast windows for differing solar data sets. And this is perhaps not their biggest contribution yet, so we expect good things, but these results are super important. So super well done, solar drag team. And I'll give it just a second, a little bit of applause as we're highlighting all of our amazing solar drag team. Congratulations.
Excellent work. All right. Here we have the much awaited and heralded Heroic Comeback Award. So Heroic Comeback is an acknowledgement that when discovering something genuinely new, you have to first fail. But that's only half of the story. Simply failing isn't enough. Getting back up, learning, evolving, and trying again is how legends are made. And who does it go to, Sarah?
Yes, this award goes to our Lightning team. So Lightning has persevered in the face of great difficulties with their resources and data. This team has had a hard time with setup and elements out of their control that make their project especially challenging. Being with them for a bit and knowing firsthand the additional technical difficulties, I think they are perfect for this award. So super well deserved. Congratulations, Lightning team.
Well done. All right, this is one of my favorites because, you know, collaboration is really what FDL is all about. And as we said at the very beginning, FDL, among other things, is about bringing different disciplines together, putting together these interdisciplinary teams and watching these teams do extraordinary work. So the Collaborative Spirit Award is a representation of FDL's beating heart, interdisciplinary research. It supports the idea that to achieve great things, 2 or 20 minds are better than one, and the exchange of knowledge is key. Sarah, who got the Collaborative Award?
So this one goes to the Moon for Good 3 team. This was a very hard one to decide, but you have pulled off a very hard task delivering the great results FDL expects while being only a team of 2 researchers. You've been subject to the same pressures as the other FDL teams, yet only half the number of researchers. And to overcome this limitation, you worked exceptionally well together, recognizing each other's strengths and weaknesses, and complementing each other in the research that was carried out. On top of this, your team maintained excellent communication with your team leads, taking on board feedback and changing your workflows when necessary. Your research would not have been possible without the relationships that you have built together and the communication skills that you have used. So congratulations, Moon for Good 2 team. You guys did really amazing. And because this was such a hard decision, we also felt that it was important to make some honorable mentions as well. So I'd also like to just mention the Lightning and Solar Wind team. You guys did extraordinary work and demonstrated a collaborative spirit. You also rebounded from a couple of Wi-Fi outages during a talk and supported your team members. And you basically, between the 2 of you, showed great collaboration from the get-go. And then Constantine, you in particular, were also recommended by faculty as you have helped with the organization and communication and processes within your team. So we just wanted to say congratulations and well done. And Bill, back to you.
All right. Thank you very much. Well, you know, the collaboration, you know, none of what these teams achieve would be possible without collaboration. It's collaboration between the researchers, it's collaboration between the researchers and the mentors and the faculty, and also with the teams and our partners. So it's really all about collaboration. As Sarah said, that's why it's so hard to single anyone out, but you've all been incredibly collaborative. And as noted, that really is the beating heart of the FDL program. So we've added a new award this year, and that's really recognizing how, because of the virtual environment that COVID has compelled us to undertake, that you know, people are working around the clock. I think the FDL program covered like 9 different time zones, if I'm not mistaken, in this year alone. So the Night Lab Award is for team members that went above and beyond, working both night and day and weekends and time zones spread across the world to make things work. So who are the winners, Sarah?
Yes, so for this year's Night Lab Award, we have Fexen, and FXN, there's a lot to be said about you. You were working across multiple different time zones. You are in Malaysia and you still operated on all different time zones. And I have here absolutely amazing and hardworking in midday, overnight, always smiling and happy to help. So congratulations. We also have Julia and Emmanuel who were working hours to be able to work with their leads in the Pacific time zone. Ganesh, you were noted as working around the clock, as well as Stefano, who is not pictured up here, but I'm going to do a shout out as well for being up early to be able to work with the folks over in Europe. So congratulations to all of you. And we know virtual is hard and you guys made it work.
Absolutely. Well, you know, and when we do the FDL in person, which we hope next year we'll be back in person once again, you know, the teams still work around the clock, but at least they're all together and they're all in the same time zone. So what you've all done and the challenges you've had to overcome to work as a team, never having sat face to face with each other, is really extraordinary. All right, the last award for today, which was actually debuted last year in the FDL program, is the so-called steely-eyed operator. And so in every FDL project, there's a moment where everything can go wrong. This is the implicit contract of high risk, high reward research. If you don't go through this, then your work isn't new enough. Remaining clear-eyed and clear-headed in this moment is rare quality, and without it, FDL wouldn't deliver. The steely-eyed operator acknowledges the efforts of a faculty member who has regularly been the calm voice in the storm, quite literally. So Sarah, who is our steely-eyed operator for FDL 2021?
Yes, we have two. So we'd like to acknowledge Nadia and Frank. Nadia in particular has led the Lightning team, and their team overcame some challenges that have been first for FDL. And obviously with the results today, did a fantastic job. And Frank, who managed to help out two teams. But not only that, Frank has been an absolute resource for a number of teams, helping with many different hurdles, and has been a researcher and then moved on to being a mentor for the last several years. So it's just been an absolute resource for FDL in general. So congratulations to both of you.
Congratulations, Nadia and Frank. And Frank has been, you know, with us from, I guess, nearly the beginning of the program, right? I think, in fact, when the program started, he had more hair, if I'm not mistaken. I don't know. But anyway, we're very grateful to you both, and thank you. And of course, you're also representative of all the mentors and faculty who've given so much unbelievable support and help to the teams this year. So thank you so much and congratulations. And with that, Sarah, I think it's time to turn the podium over. We are honored to have with us today from NASA Ames Research Center, David Korsemeyer. David is the Associate Center Director for Research and Technology at NASA Ames, and NASA Ames and the SETI Institute have been partnering on FDL from the very beginning. David, we're very grateful to have you with us today. Thanks so much, and we'd love to hear your perspectives on the FDL program and what you've seen and heard from the teams this year.
Thanks, Bill. As is typical, it's been a phenomenal year. I can't tell you how pleased I am that we were able to continue during the time period of COVID. The second year in a row that's been virtual, but this year we've got 7 teams, you know, the 2 Helio, 3 Earth, 1 Astronaut Health, and 1 Lunar Resources, and it has been just a phenomenal spectrum of various applications of AI/ML to kind of NASA-wide, NASA-esque government big problems. It's just been really impressive, and I want to thank the whole set of teams. The what's the phrase? So flippin' cool set of teams now that have done such a great job. I think one of the real values of it being done virtually, in some sense, is that now we have access. We have these you know, online archives of the recording of the presentations that we can go back and mine through, and I can ship around to other NASA folk to make sure they've had a chance to look at them and see the real value of these different approaches. It's been really quite impressive. You know, we're on our 6th year of doing this, and I am amazed that every year it does actually seem to get better. And it's done in partnership with a lot of different groups and a lot of different organizations. And specifically, I want to call out Google Cloud, who, you know, provided all the cloud computing resources and was a huge element of sponsoring this activity. It was tremendously helpful. We've had other governments, Luxembourg Space Agency. We've had within the U.S. government, USGS, Lawrence Berkeley National Lab, UCAR, DOE. We've got tremendous academic and industrial partners in MIT, Intel, Lockheed Martin, Trillium, IBM, NVIDIA, Mayo Clinic, Planet Lab, now just Planet, sorry. And, you know, of course, hey, we do give you credit, Bill. SETI has been instrumental in making this work, and it's continued to be incredibly viable. I think one of the really interesting components of this has been the fact that it has improved on a year-by-year basis as the technologies and tools become much more capable, and the skills of the students, the faculty, and the advisory boards have had some experience dealing with this. We're starting to see even more and greater impacts and technical value coming out of this activity. I've heard of degrees coming from this. These are the initiating concepts that have led to advanced degree program theses and dissertation classwork. So we're just thrilled to death to see this happening across the board. I want to say that we're kind of in the golden age of applying AI ML, and it's not really AI, but because it's not planning and scheduling, but it is ML, and it is a incredibly powerful tool, and we're learning through application to all these various data sources, of which NASA data is some of the most heterogeneous you're going to get out there, of how to apply this cloud environment with these classification machine learning tools to basically give us interesting insights and results. And hopefully these initial results will be validated through secondary analyses and applications, and will verify and validate that they are truly the insights and breakthroughs we hope they are. I want to thank all the participants. I want to thank again everybody who's been involved on the sponsorship and support side. I really personally do miss coming out, Bill, and seeing all this in person, because we've only been able to dip in a little bit, and that's one of the reasons I am pleased that a lot of this is online. Again, thanks to the whole of the FDL 2021 community. Let us all hope and pray that we are in person next year and can do this in Mountain View and see you all in person in the right time zone.
In one time zone.
In one time zone at a time.
Absolutely. That's terrific.
Thank you very much for everything, everybody, and thank you, Bill and team.
Thank you so much, David. We really appreciate that, and I know the teams appreciate hearing from you. And thanks for your time and joining us. And it really has been a journey, continues to be a journey, and we've many teams, building on the work of prior teams, and we can see that there can be a continuation of this in future years. And Scott, maybe before our final closing remarks, you've been with us from the beginning. You've sort of seen the evolution of what's been going on in FDL, and of course, Google's been instrumental in enabling the compute that makes it all possible. What's your takeaway and your vision going forward here?
The program is just so flipping cool, Bill.
Here we go.
If you look at it, I just think that what everyone's done here in the last 4 years, I mean, James is an inkling of, you had an idea, you and Sarah, when I first met you all in 2017, you said, what happens if we could tap into some of the best in Silicon Valley, get you all to work together? I mean, all the competitors are helping you out, right? Think about that. And then you get Silicon Valley to work there, and then David's putting up with us and saying, how do you get this AI stuff to actually intersect with NASA, which is arguably the most conservative, some of the best science in the world. And I think you've now shown how many of these projects, there's 50 different projects, right?
Yeah.
Total. Yeah. And it's just, I think we're just getting started, as Lika said. And, or I guess Dana would say earlier that we're sort of like a 6-year-old, right? Or something like that.
Right.
And I think it's just see where this is going to go. And I hope that over time, AI will be a tool of science. And it'll help us answer some of the deepest questions, David, by working with NASA. And I think by working together, we're going to change science with this.
Absolutely.
Very much true.
David, I don't know if we'd get in trouble with headquarters, but what we really should do is put a sign on the entrance, that big sign right out in front of the Moffett entrance to Ames says FDL 2021, so flippin' cool.
Let's talk about doing that for 22. We'll see.
Absolutely. All right. Well, thank you all so much. Let me turn this back over to Sarah, and also our director of the FDL program, James, is back with us. So let me turn it over to you, Sarah and James, to wrap things up for this year.
Yeah, James, do you want to go ahead and close this out here and have some remarks and reflections?
Yeah, I always get a little bit weepy at this point, depending on how much wine I've had. I just, yeah, so flipping cool, like a really unbelievable, really, you know, it's and it's so exciting as well. And I find it's kind of this sort of this, you know, crazy discourse, because we're talking about these problems which are so, you know, wild and difficult and challenging. But we have this technology, and we have this ability to actually make a big difference. And I've been trying to make an impact my whole career. Like, started off in sustainability and trying to figure out how to move the needle, and for so many years just not being able to. And so personally, you know, just to be able to see this work and see the impact that we can make, you know, it's great. It's a great moment. So I just wanted to say thank you to the researchers. I mean, you've worked so hard. It's unbelievable. Just next level stuff. And as Dave said, it gets better every year. We whisper that because we don't want to offend the teams from last year, but it's amazing what you've done. But also faculty as well. You guys, I mean, really, it's incredible what you've been able to the level you've been able to get to, the vibration state we're now operating at. Yeah, let's turn some heads. Let's get this work out in the world. Let's get it up for other people to build on, and let's see if we can make a dent in the universe. So that's my closing thoughts. Just thank you so much. Thanks to NASA. Thanks for the great questions, and we'll see you all next year.
Wonderful. Thank you, James. And Sarah, do you want to say just a couple of words about you know, what's coming next? Because I guess we'll also have recorded versions of these presentations available, and of course we've got the proceedings that will, you know, come out I guess in a month or two.
Yeah, great. So I'll go ahead and close this out with some next steps and just some thank yous. So our teams do continue on the work. We do put these recordings out publicly. We also share tech memos. Our teams continue to work on them and go to different conferences, as well as work towards publications. So definitely this is not the end. It is only the beginning. So I wanted to share the photo of everyone at our boot camp where we started off. And I can't believe that we're already here at the end of FDL, but I'm excited for all of the things to come.
I think next year we do have to investigate the space-time distortion that happened during FDL. Like, this is a definite thing that happened.
Blip, yes,
we need
just
to
a blip.
figure out how to measure it.
Some sort of gravitational wave.
Yeah.
So we wanted to say thank you to everyone at the SETI Institute that has been working behind the scenes. We've worked with Rebecca, Lee, Debbie, Yvonne, and Armine, as well as Jasmine, and of course, Bill and the rest of the SETI Institute who have made this possible. And also from the Trillium side, we have a wide range of our team here. So James and myself, as well as Ann Shile, Cormac, Leo, Sarah, Jody, Freddie, John, Gonzalo, Richard, Yaren, and I think I got everybody there. So thank you for all of your work through FDL. And with that, I think we are closing now. And I just wanted to say again, thank you to our audience today. Thank you to our partners, the SETI Institute, NASA, and just all of our researchers and faculty. Thanks for tuning in.
He's going to say,
Sarah, have a round of applause for the researchers. That's fantastic. That was amazing.
Yeah, absolutely incredible, and especially under the circumstances, you guys are amazing. So hats off to you. Thank you so much for your extraordinary work. And yes, we'll see you all next year. And what will happen next year is a whole bunch of the participants will come back as mentors.
Well, that's right. That's when you say it's the Hotel California.
It's the Hotel California. You can check into FDL, but you can never leave.
Awesome. And with that, I think we can go ahead and close. So thank you, everyone.
All right. So flipping cool. Bye, everybody.
Bye-bye.